Hi everyone, how are you doing all? Okay, so today we are going to start a very exciting topic which is DFS and its application. And we will do all the PYQs which are there in the gate, okay? So let's get started. So this is going to be very interesting session in the sense that you will get to know all the PYQs that are there, and there are many interesting applications also. So you will get to understand all the applications with the PYQs, okay, with the help of PYQs. So let's get started. Okay, let me just start now. Yeah. So the very first thing that we need to understand DFS, that what are the graphs, right? So let me quickly go over that what are the graphs and all. So what is the graph? A graph is basically not this. I mean, for us at least, it is not this, right? So we are not looking at this as a graph. We are looking at what kind of graph? So we want to look at these kind of graphs, right? So in this particular session, we want to look at these kind of graphs. Okay, cool. Now, uh, now why graph are important that much? I mean, we know that we want to study graph, but let's just see that why these graphs are that much important. Because graphs show us all the time, which means if you even talk about Google Map, okay, this Google Map, like this must be some graph algorithm, right? Because this Google Map or any country, city, street, these can be these can be seen as a graph, right? So basically this Google Map is just like a graph. So this is one application of the graph. And what are the other applications of the graph? So for example, let's suppose you talk about any networking website, right? For example, you talk about Instagram, you talk about Facebook, you talk about anything, right? This is also a graph. So basically these networking websites are also graph. What are also graph? This web page, let's suppose this is web page A. Okay, this is web page, this is web page A, this is web page B, and B is going to web page C, right? This is website C, website or web page or something C. So basically if A has some link that can redirect you to B, and then B has some link that can redirect you to C, then also you can say that these all are things are the under graph, right? So this is also the graph. Similarly, in the compiler design, you will see control flow graphs. So in the compiler design also, you will see the graphs. So graphs are everywhere, right? Graphs are everywhere in all the subjects. Also in many applications, the graphs are there. So that's why we want to study graphs. And in particular, this session, we want to see the PYQs with the applications of DFS. So before that, let me quickly go over what are the notations. So this is a graph, then we will say G is a graph, V is a set of nodes or set of vertices, E is the set of edges, okay? So that's how we will represent a graph. Now, we will say this is an undirected graph and this is a directed graph. So this is an undirected graph. Undirected graph means that you don't have any directions here. You don't have A to D as a particular direction. Here you have a fixed direction that you can go from A to D only. Okay, I hope all of you might be knowing this. Right? Okay. So Prasanna Kumar is asking, sir, it is there in the DA paper also? So I think in DA paper they haven't mentioned this, if I remember correctly. They haven't mentioned the graph algorithms, if I remember correctly. You can just check it out. Okay. For the GATE DA syllabus, let me just tell you that what is the GATE DA syllabus. In the GATE DA syllabus, basically they have mentioned the algorithm, right? And in the algorithm itself, they have mentioned, let me just tell you that what they have mentioned. They have mentioned the traversals, yes. So in the GATE DA syllabus also it is there, because in the GATE DA they have mentioned the traversals. So as you can see on the screen, this is the GATE DA syllabus. So if you are from the GATE DA background, then also you should watch this lecture, because they have mentioned this traversal techniques, right? And shortest path. So they have mentioned this basic graph algorithms, where the traversal technique, which means DFS and BFS. Okay, they mentioned this DFS and BFS in the GATE DA syllabus. Okay. Now, in the undirected graph, like if you talk about the connectivity, which means, see, the graph can be undirected or graph can be directed, right? Now, in the undirected graph, we will say this is a connected graph and this is a disconnected graph. Why? Because this graph is not connected, which means that like this whole thing is a graph, but this is having two components. Components means this is a one part of the graph, this is another part of graph, which means if you want from here, Can you reach to here? No, because there is no path from here to here. That's why this is called disconnected graph. This is called connected graph. Okay. This is the story of undirected. What about the directed? In the directed, we have something called as strongly connected. What is this strongly connected? Strongly connected means everywhere, like from any pair of vertices to any pair of vertices, there is a path, which means I think the definition is here, that there is a path from every vertex to every other vertex, right? This is every other vertex. So if there is a path from every vertex to every other vertex, you will say it is strongly connected. You will say it is a weakly connected graph if there is a path from every vertex to every other vertex, ignoring the direction of the edges, right? If you ignore the direction of the edges and still there is a path from every vertex to every other vertex. For example, is this graph strongly connected? Tell me, is this graph strongly connected? What you will say? See, this is a topic of graph theory. That's why I will just quickly skim over this. Okay. This is by the way, this is a topic of graph theory only. This is a topic of graph theory. Okay. You will see that in the graph theory. I'm just quickly telling you. Okay. See, is this graph weakly connected or strongly connected? What do you think? This graph is weakly connected or strongly connected? See here, can you reach from this vertex? Can you reach from this vertex to this vertex? No, right? But if you ignore the edges, then you can reach. So that's why this graph is weakly connected, right? If you ignore the edge directions, okay? If you ignore the edge directions, after that, if you can reach, then this graph is called weakly connected. Okay. Now let's just see how we can store the graphs. So we need to store both the set of edges V and E, okay? So which means if this graph is given, then we need to store this graph. Now how we can store this graph? We need to store that using some data structure, right? So what kind of data structures we can use to store this graph? There are two popular data structures. One is called adjacency matrix. It is saying if you want to store this graph, then what you do, let's suppose this is an undirected graph. If you want to store this, then you write all the vertices in the row, all the vertices in the column, right? All the vertices in the row, all the vertices in the column. And if there's an edge between A to D, let's suppose there's an edge, then write 1, otherwise write 0. Okay. I hope you might be knowing this. This is called adjacency matrix. If this is undirected graph, then there's an edge from A to D and also D to A, right? Because this is undirected. So A to D there's an edge, then D to A there's an edge, right? Okay. Let me just ask you, in undirected graph, can you say that adjacency matrix is symmetric? So in undirected graph, can you say adjacency C just a second. Okay, tell me, adjacency matrix is symmetric? If the graph is undirected, then the adjacency matrix is symmetric. See, the answer is yes. Why? See here, this is symmetric. I mean, this is 1 and this is 1. The matrix is symmetric, right? And why that is the case? Because if there is an edge from A to D, then there is an edge from D to A also. So that's why this is yes. So what you will say? That yes, right? Yes. Okay. And what is the adjacency matrix in case of directed? In case of directed, the adjacency matrix will look like this. See here, if this is, let's suppose, the directed graph, then if you want to draw the adjacency matrix of this particular graph, then you will say something like this. This is A to D, so you will write it here 1 because this is A to D, and then D to B is here, D to B is here. See here, D to B, right? You can write it as 1. So basically, whenever there is an edge, you can write it as 1, right? Whenever there is an edge, you can write it as 1. Okay, cool. Now let's move further. This is adjacency matrix representation. So first we have seen adjacency matrix. This is adjacency list. Okay, adjacency list representation. So what this is saying? This is saying that if there is an edge from A to B, okay, if there is an edge from A to B, then you write it in the list. A to B, there is an edge. If there is an edge from A to D, then you also write. So which means all the neighbors of A. See, these are all neighbors of A. All neighbors of A. These are all neighbors of A. Understood? Which means all the neighbors of A you will be writing in a linked list. Similarly, if B is here, then all the neighbors of B, which means A, C and D, right? So A, C and D you will be writing here, right? So basically you can say that here this edge is making A and D neighbors, right? A and D neighbors. This edge is making A and D neighbors. So that is why this edge, because of this edge, there will be D here, and because of this edge only, there will be A here, right? So basically, just because of one edge, there are two nodes, right? There are two nodes here. So that's why if the number of edges are E, then can you tell me what is the number of nodes here? The total nodes here in this circle, if the number of edges are E. See, because of every edge, there are two nodes, right? You can pick any edge, A to B. So you will be writing this here, you will be writing B to A, right? You will be writing this here. So because of every edge, there are two vertices. So if I say that these are E, these are the E number of edges. So how many total nodes are here? There will be 2E, right? 2E. That is also handshaking lemma if you know it from the graph theory. Okay, handshaking lemma, which says that summation of all degrees is basically 2E. Anyway, don't worry about it. We are not concerned about the graph theory. I'm just telling you few things because it might be required. Okay, it might be required for us. For that purpose only I'm telling you. Otherwise, I could have not told this handshaking lemma. But let me know if you have understood this. Okay. So what I'm trying to say here is that if you have this as a, let's suppose, adjacency list, then in that case you will be having this kind of representation, right? Okay. So these are the all neighbors of A. Now you tell me if I say degree of let's suppose A, you understand about degree? What is the degree? The neighbors, right? The count of neighbors. So this is degree 2. If the degree of A is let's suppose D of A, or maybe let me write like this, is degree of A only. I mean, this is the degree of A. Okay, maybe X or something. Then how many nodes are here? Can anyone tell me how many nodes are here? If the degree of A is X, then how many nodes are here? Here it will be X only, right? If the degree of B is, let's suppose, bi, then how many nodes are here? This will be bi. I mean, these are the list of all neighbors. So that's why this list is equal to the degree, right? This list is also equal to degree of B. This list is degree of C. This list is degree of D. So basically, if you sum all of this, then you are essentially summing up the degrees, right? So that is why it is 2E. That is the only reason I've said it is 2E, because you are essentially summing up the degree. But here, if you notice in the directed graph, what is happening? This is A to D, right? So this is just one edge. I mean, earlier also it was one edge, but it was contributing in A also, in D also. But here, this A to D will be there. But since D to A is no edge, that's why D neighbor is not A. So that's why you will not be having A here. There is no A here. Okay, no A. Understood? Here you have D, but here you don't have A. Okay, here you have D. Here you have D, but here you don't have A. What is the reason? Because A to D is an edge. A to D is an edge, but D to A is not an edge. So that is why you have D here, because D is a neighbor of A. But D neighbor is not A. D neighbor is not A. Okay. A neighbor is D, but D neighbor is not A. I hope you understood. Okay. Cool. Okay. Now let me know if adjacency list and adjacency matrix both are clear to everyone or not. Okay, how to represent using adjacency matrix, how to represent using adjacency list. Cool. Now, are you ready to solve this question? Let's just solve this question. What this question is saying, that how much space adjacency list will be taking, okay, and how much space adjacency matrix will be taking. Let's suppose V is the total number of nodes, E is the total number of vertices, total number of edges. Then it is very clear. It is very clear that adjacency list will be, okay, matrix, for the matrix at least it is very clear, right? Order of V square. Okay, order of V square. So Shashank is asking what to do if there is a cycle on a particular node. If there is a cycle, you can have A to A. Okay, you can definitely have A to A if there is a cycle. Okay, because that is also one edge. That is also one edge. So you can have A to A. Okay. If there is a cycle, then you can definitely have here also. And in the adjacency matrix, you must be having this edge one, right? A to A, this edge one. If there is A to A is a cycle. Okay. If there is self loop, then you can have something like this. Okay. Cool. Now tell me, is this clear to everyone that in the adjacency matrix, the space requirement is at least V square, right? Okay, what is the space requirement for adjacency list? What is the space requirement for adjacency list? Can anyone tell me? See, what is happening in the list? You are having one node, and here you are writing all the neighbors, right? All the neighbors. So how much all of this? How much all of this? how many nodes you are, how much space you are having here? 2e, right? 2e. In case of directed, actually it will be e. In case of undirected, we have 2e. Anyway, it doesn't matter. In case of directed, actually the one edge is anyway contributing only to one node, so there will be e or 2e, doesn't matter in asymptotic sense. So anyway, so I'm writing 2e. Okay, and this, how many this are there? How many this is there? These are the number of vertices. So v, right? So I think v plus e, it will be taking v plus e, right? V plus e or v plus 2e, doesn't matter. So you can write v plus e. Okay, so it will be taking v plus e. Great. So now we know here it will be taking v plus e, here it will be taking v square, right? Order. So let me write order of this. Now tell me, suppose if someone asks you that you want to check. Suppose if someone asks you that you want to check whether a given edge is in the graph or not, which means someone asks you that some graph is given to you, some complicated graph is given to you. This is A, B, C, D, E, F. Someone asks you whether E to C to E, okay, C to E edge is there or not. Then how you can check using adjacency list? This is the time, okay? These are the time complexity. How much time you will be taking using adjacency list? If someone is asking C to E, you will go to the C list, right? List of C. Whether E is there, right? Maybe D is there, maybe F is there. You will be going to the list of C, right? So maybe E is there. So how much maximum time you can take? Can anyone tell me? Okay. How much maximum time you can take? So see here that it will be taking degree of, let's suppose it is u, then degree of u, because this list is as long as degree of u, right? This list is as long as degree of u. So that is why if I just ask you this, the test if this, then how much time you will be taking? This is degree of u, right? Okay. So here basically here you will be taking degree of u. Here, how much time you will be taking? This is interesting. Here, how much time you will be taking? Here you will be taking order of 1 only, right? Order of 1. Why? Because in just constant time, you will go to row of u and column of v, right? You will go to row of u and column of u. You will check whether this is 0 or 1, right? This will be constant. So you can say here, if I just fill it little more, then you can say here you will be writing order of, okay, for this particular row, you will be writing order of degree of u, right? Order of degree of u, and here you will be taking constant time, order of 1. Now they are saying list v is never. Actually, this is most important. Okay, this is most important operation. Okay, this is most important operation we need again and again. We need in graph traversals. So now you tell me how much time you will be taking. Okay, you will be taking in listing out all the neighbors of this v. This is the most important thing that we will be doing again and again. We will see, okay, in the DFS we will see that we need this again and again. Okay, in the DFS we will say, okay, go to the neighbors of V or something like that, right? So in DFS we need it, in BFS we need it. So how much time you will be taking here in the adjacency list if you want to list all the neighbors? How much time? Can anyone tell me? Yeah, so you basically you will be taking degree of v, right? Degree of v. So let me write it 1 plus. Let me write it 1 plus 1 plus. The reason being is that if this degree of v is 0, then at least for anything you take the constant time, right? So that's why, just to avoid this. So whenever I write degree, I will always be writing 1 plus. Okay, cool. So you will be taking basically degree of v time. Now you tell me, in case of adjacency matrix, if you want to list out all the neighbors, how much time you will be taking? This is interesting. In case of adjacency matrix, you will be taking order of v time, right? In case of adjacency matrix, okay, in case of adjacency matrix, you will be taking order of v time. So if you want to basically if you want to do it, so let me Okay, we have done till this point. If you want to list all the neighbors of V, then you will be taking order of V time here, and here you will be taking degree time, but degree can be as greater than as this V, right? This is anyway degree, right? This is degree of, you can say U, but degree of U can be as large as V, right? So that's why I'm just writing upper bound. Okay, it is not wrong. Okay, it is not wrong. I'm just writing upper bound because this is order. Okay, this is big O, so that's why this works, and this is degree of V. This is also not wrong. Okay, anyway, like that we can also answer these three questions. Okay, if I want to insert some edge, then how much time you will be taking here? Order of 1, because you can directly insert here also. You need to do 0 or 1, from 0 to 1, so that's why order of 1. If you want to delete, then it could be as long as order of V or the degree of U or something, and here it will be order of 1 only, because you need to go from 1 to 0. Okay, like that. Cool. So these kind of operations you can do. Okay, so someone is asking that, sir, can you please tell in the graph shortest path mentioned in the data science syllabus, which topics are they? So they haven't mentioned the specific topic. Okay, in the data science syllabus, they just said shortest path. So shortest path means Dijkstra and Bellman-Ford. Okay, in the gate DS syllabus, in the shortest path, they have just said shortest path. So it means the Dijkstra and Bellman-Ford that are there as an standard algorithms. Okay, so you can just see the Dijkstra and Bellman-Ford. That is enough. Okay. Now when we talk about the dense graph, okay, when we talk about the dense graph, then the number of edges could be V square, which means the graph is so dense that there is an edge between every pair of vertices. So here the number of edges could be as good as V square. Here in the sparse graph, it could be maybe just V or something. Okay, so basically, if someone asks you that is E greater than V or V greater than E, then what you will say? Let's suppose someone asks you that is E greater than V, or maybe let me write it like this: is V greater than E always, or maybe E greater than V? Then you will say that, okay, then this E and V can be even equal, right? Can be even almost equal. So basically, whether which is greater, which is not greater, or maybe if you compare between V square and E, then which one is greater? See, this E is basically, okay, minimum it can go to V, and maximum it can go to V square. So if someone is asking you V square versus E, which one is greater? Then you will say it will depend on the graph itself. If the graph is dense, then E is as good as V square. So basically, if someone is asking you V square versus E, okay, V square versus E, now you will say which one is greater? Now it will depends on graph. Depends on graph, right? If the graph is sparse, then which one is greater? Then basically you will say that E is same as, okay, number of edges is, or maybe let me just write E is same as V. If that is dense, then number of edges could be as good as V square. Okay, understood? So it will depend on the graph. If someone asks you, let's suppose someone asks you that which one is greater, let's suppose V log V is greater or E square is greater, oh sorry, E is greater, then what you will say? See, again it depends on the graph, right? Depends on graph. Let's suppose if it is a sparse graph, then E could be almost same as V, then obviously V log V is greater. If it is dense graph, then E could be almost same as even V square, then E is greater, right? E is greater than V log V. Is this understood? Okay. So Mohit is asking that, sir, in the list, how we are finding a vertex in just order of 1? Which one? you want to list out all the neighbors of V, right? So in the list, how much time you will be taking if you want to list all the neighbors? It is just degree, right? It is just degree of V. So that's all. It is just degree of V. Okay. So let me know if that is okay to everyone. Cool. Now let's go to the next slide. See here. Now if I just ask you which one is greater in between this. Let's suppose if I just ask you log V and log E, which one is greater? Which one is greater, log V and log E? If I just ask you versus, then what you will say? See here. Now interestingly, in the sparse graph, I'm assuming that is connected graph. E is basically, E could be just B, right? Now log V and log E are same. And in the dense graph, even if E is V square, then also log E and log E and log V are same, right? So basically when it is log, then it doesn't matter about the graph. When it is log, it seems like it doesn't matter for the graph. Okay, if it is not log, then it will matter because that could be the relationship, right? But if it is log, then both are same basically, right? Both are same. Okay, great. Now let's just see tree versus graph traversal. So in basically tree, we have many traversals. Can you tell me what are the traversals possible in the tree? What are the traversals possible in the tree? So you will say if it is a tree, then we have seen maybe in order traversal. You might have studied pre-order traversal. You might have studied post-order traversal, right? These are the traversals which are possible in the tree. In the graph, DFS and BFS are the most popular one. Okay, DFS and BFS. So what is the difference in the tree traversal and the graph traversal? What are the difference? See, the difference is in tree there is a fixed obvious start, right? I mean, you will be starting from here and this is like clearly ordered, like, okay, I mean, well structured basically, right? But here it doesn't, it does not have any order. Maybe you can start from here, maybe you can start from here. It is just a graph, right? Any start, any order, end is also not obvious. Here the end is obvious. See, if there is a no child, then you will stop, right? You will stop at this node. Why? If there is no child, you will stop. See here, if there is no child at this, you will stop. If there is no child at this, you will stop. But is this true here? No, right? I mean, you will see, okay, whether I have visited it or not, you don't know, right? I mean, you need to be a bit careful in this. Okay, so there are subtle differences between tree and graph traversals, right? Tree and graph traversals. So there are subtle differences. Okay, now let's just see DFS traversals and its applications in a great detail. Okay, in a great detail. Cool. So basically, we are in this lecture, we are going to see DFS traversals and its applications. If time permits, we will also cover BFS. Now let's just start. Okay, so BFS and DFS are two popular methods here. Okay, two popular methods here. Now suppose there is a graph that you have. Now the question is that how you are going to traverse, right? How you are going to traverse? Are you going to start from A, from this one, and then you are going to go to 2, and I mean there should be some method, right? How we are going to traverse. So what you can do, given this graph, what you can do, you have an idea, and what is that idea? Whenever you go to any node, you put that node in the bag. Okay, you put that node in the bag, and you will say that, okay, I have traversed that bag. And whenever you are popping out or whenever you are removing something from bag, you put its neighbors also. Okay, you put its neighbors also, which means what I'm saying, see here, you put, let's suppose you put 2 in the bag. Okay, you put 2 in the bag. Okay, you can put anything in the bag. You put 2 in the bag. Now if you're removing, okay, whenever you remove, you will say, okay, 2 is there. Now if you're removing, then you put its neighbors also. You put 1 and 3. Okay, you put 1 and 3 in the bag. Okay, now 1 and 3 in the bag. Now you can remove anything. Let's suppose you are removing 3. Okay, you are removing 3. You remove 3. You put its neighbors. Okay, which is 5, which is not visited basically. Okay, so you will be putting 5, and 3 is removed. Then you can again pick anything. So which means, let's suppose now you are maybe picking one, or doesn't matter, 1 or 5 doesn't matter. Now you will remove this one and put all its neighbors. Maybe 4 you are putting, right? Okay. Now you pick any node. Maybe 5 you are picking, and then you are saying that, okay, now I will remove this 5. I will put its neighbors. So there is no unvisited neighbor. So that's why that's okay. This 4 is okay, right? So there could be this traversal, right? This could be one of the traversal. Is this fine to everyone? So what is this traversal? This is saying that you put something in the bag, and whenever you are removing, you put its neighbors also. So which means, see here, let's suppose this traversal technique I am calling whatever, okay, whatever first, okay, whatever I'm seeing. Put S in the bag. If S is not empty, extract something from the bag. If V is unmarked or unvisited, okay, make it visited, and then put its neighbors. So this means put its neighbors. Okay, so this means neighbors. Of V. Okay. Now, interestingly, this algorithm, okay, can be DFS or BFS depending on the bag. Which means if this bag is stack, it will be DFS. If this bag is Q, then it is BFS. Okay. So what I'm saying here is that this bag means some data structures. Okay. If you are using stack as a data structure, it will be DFS. If you are using Q as a data structure, it will be BFS. So in that sense, we can say that DFS and BFS are twins. Twins means that exactly same, just the matter that you are using stack or queue. Okay, they're exactly same. It is just that you are using stack or queue. Now let's just get started with the DFS. Okay, depth first search. See, let's suppose this graph is given to you, and what we want to do, we want to do depth first search here. Let's just try depth first search. So what does depth first search says? Okay, we need to understand this depth first search, and then we will see its application also. Suppose at A we are starting our depth first search. So we can start the depth first search at any node. Suppose we are starting at A. You can start at B. You can start at C. You can start anywhere. Suppose we are starting at A. Okay. Is this okay to everyone? We are starting at any point. Let's suppose that it could be A. Okay. You can start at A, anything, but for the sake of example only, I am starting at A. Now what you will do, you start at A, then from this A, maybe you can go to B, right? Or maybe you can go to C, doesn't matter. And then you keep on going, okay? You keep on going. Then you from B, you will go to C. And at this C, tell me, at this C, is there any unvisited node left? No. So as you know that you have come to the C using this path, so you will backtrack. If there is no unvisited node left, you will backtrack, okay? So just backtrack here. Which means you will go to this B again, and now you tell me from this B, any unvisited node is there? Yes, there are many unvisited nodes, E and D, right? So you can go to anything. So from this B, let's suppose I'm going to D. Okay, I'm going to D first. From this D, let's suppose I'm going to F. Okay, or you can go to anything, but let's suppose I'm going to F. And then from this F, tell me any unvisited node? No. So you will backtrack to D, and then from this D, any unvisited node? Yes, E is unvisited, right? See, A is visited, B is visited, C is visited, D is visited, F is visited, and E is unvisited. So from this D, E is still unvisited. So you will say E. Okay. So maybe I can write it like this. First you are going to F. Then you are going to E. Is this okay to everyone? That how we are writing this? See, given this graph, can you do the DFS traversal? Easy, right? You just keep on going. If there is no further, then you just backtrack, right? You just backtrack to from wherever you are coming. Okay. And then keep on going. If there is no further, you backtrack. Now let's just understand a thing called discovery time and finish time. Okay. Discovery time and the finish time. Let's just see discovery time and finish time of DFS. So see, you are starting at A, right? Let's suppose I'm saying, if you are starting at A, let's suppose I'm saying that this is start time maybe 1. Okay, 1. You are starting. So let's suppose this is 1. Oblique. I will be writing end time also here. Okay. Currently I don't know the end time, so I'm just putting it as oblique. Okay. Now, whenever you do, you basically explore any new node. Let's suppose this B. I will say this is 2, then this is 3. Now you will backtrack, and then before backtracking, see, whenever you are backtracking, you're sure why you are backtracking, because you know that this C is not anymore needed. I mean, this from this C you cannot go from anywhere else. So that's why you're backtracking on C. So whenever you backtrack, that is called, this is end of C, which means the C is finished. So the finish time I'm writing as incremented one, which means 4. Okay. Now you go here, and I'm not writing 5 here because it is not finished, right? So you go here, and then you let's suppose you are going to D. So D I'm reaching at 5, then you are reaching at this 6, and then you will backtrack. So before you backtrack, write the end time also. So this is 7. You go here, this is 5. Now are you backtracking currently? No, right? So you will go here, this is 8. 8 is the starting time of E, and now you will backtrack. So this is 9, this is now 10. Okay, you are backtrack, this is now you are about to backtrack, this is 12. Let me know, is this discovery time and the finish time okay to everyone? Okay, because this is going to be very interesting and very needed also, very much needed, discovery time and the finish time. Okay, you will see in the gate PYQs also, many times they have used this discovery time, finish time, these kind of terminology. Okay, maybe I can just show you. See here, this discovery time, finish time, they've used these kind of terminology. Let me know if discovery time, finish time is okay to everyone. Okay, so basically, given this graph, you can basically tell me that what are the discovery times and what are the finish times. Okay. See, this is little important to understand the discrete time and finish time. So that's why I'm just asking you. If there is any doubt, you can currently let me know, because it is important. Okay. Cool. So if you have understood this, then we can move further. Okay. Okay. So let's just move further if you have understood this, right? Yes. Okay. Now, can you run DFS on this? Yes, easily, right? Let's suppose I'm starting at S. You can start from any point. Let's suppose I'm starting at S. So let's suppose I'm saying 1. You can say 0, or this thing doesn't matter. You can say the 0 or this thing. So let's suppose I'm saying 1. Then you are going to, let's suppose A. You are going to A. Okay, Kavya is asking, will there be different times for different nodes in different traversals? Yeah, that could be that could be different. Like, I mean, in this previous example, if you start at A, and then if you go to F directly, then there will be different times, right? There could be different times also in the different traversals. So for example, from this S, if I go to A, then it will be 2. If I go to B, then B will be 2, right? Then if I go to B, then B will be 2. Okay, anyway, so you are going to S to A. Let's suppose this is 2. Then let's suppose you are going to S to A, then A to D, then this is 3, right? And where else you are going? Okay, from D, let's suppose you are going to G, then this is 4, and from this G there is no one else, so this is 5. You backtrack, this will be 6, because you are going to back, whenever you are going to backtrack, then only write the finish time. Okay, and now at D also you need to backtrack, because there is no outgoing edge. At A you can say you can go here. So at 7 you are going here. Now at 8 you are going here. At 8 you are going here. Okay, now there is no more you can say the nodes which are unvisited, so you need to backtrack 9. From here, this is the node, so here also you need to backtrack. This is 10, and then this will be 11, right? So that's how you can write the discovery time and the finish times. Okay, discovery time and the finish times. Now there is also something called DFT. DFT means depth first tree, which means if you are going from S to A first, then you write S to A. Okay, then from A, this is 2, this is 3. Okay, so from A you are going to D, right? So write A to D. Okay, and then where is 4? Yeah, 4 is here. So then you are going to G, so this is G, and then where is 5? 5 is this itself, this is 6 itself, and then where is 7? Okay, this. So basically from this D you are going to A, and then from A only you are going to B. So basically from A you are going to B, right? Okay, and then that is the tree that you are having. So this is called depth first tree. depth first tree. Okay. Can we go to SABDG? SABDG. Yeah, you can do anything. Yeah, SABDG. Yeah, that is also fine. Right. So that is also fine. So there are many DFS traversals possible. So for here also, can you write the DFS traversal? I think you can write, right? So let's suppose you are starting at some node, maybe at U if you are starting. So if you are starting, then maybe you can go to V and then Y and then this, right? So you can here also you can write. Now, interestingly, in this graph, you cannot reach to this particular component, right? I mean, if you are starting at this U, then there is no way you can reach to this. Or if you are starting at W, then there is no way that you can reach to this U. Okay, so which means it may be possible. For example, if I run the DFS here, then let's suppose this is 1. Okay, this is, let's suppose, 2. So this is 1, and let's suppose this is 2, and I'm going here. So let's suppose this is 3. Okay, and this is 4. Then you will backtrack, so that's why it is 5. You will backtrack, that's why it is 6. You will backtrack, that's why it is 7. You will backtrack, that's why it is 8. Now this is not yet visited, right? So that is why you need to visit this also. So basically, at 9 you will go here, at 10 you will go here, 11 that is a backtrack, 12 that is a done, right? So basically you can write something like this. So it is definitely possible that in one go you might not be able to visit all the vertices, but that's fine. The remaining vertices, the remaining component, you can visit in another go. Okay, cool. So this is one possible times that are written here. Okay, yeah. So I think our times and these times are matching. So 1827, something like this, right? So we have also, I think, traversed in the same way, 1827. Yeah. Okay, cool. So these are the discovery time and the finish times for this particular graph. I hope that is fine to everyone. Now, how to implement it? See, for every node, what we are doing? Tell me, for every node, what we are doing? We are just running, basically, let's suppose this is the graph and we want to implement, right? So what we are doing for every node, we are saying, let's just go to the neighbors. So for every node, we are calling DFS, which means that we are saying that, okay, at this U, if you want to call the DFS, then this DFS of U will be calling, okay? See, this DFS of U will be calling to which thing? It will be calling to DFS of, let's suppose, V, right? And this DFS of V is calling to DFS of U, DFS of Y, let's suppose DFS of Y, and then this will be calling to DFS of X. Okay, I hope that is visible. DFS of X. Okay, so that's how the calls are happening. Are the calls clear to everyone that how the calls are happening? This is DFS of X. Okay, so that's how the calls are happening. Now what will happen? Now this X will say that, okay, I'm done. X will say I'm done. Now this will go to Y, and then this will go to V, right? And then I think everything is done here. Now the next thing that you will be calling is DFS of W. That will call to DFS of Z. Okay. So what is the time complexity here? See, you are just having one function call, and that will keep on calling something else. So basically, it seems like for this, what you are doing for this. You are calling your neighbor, right? You are calling all the neighbors. If this neighbor is visited, then you will not call. So which means you are doing something like this, that you will say that, okay, you will go to the adjacent of this. See, you will go to the adjacent of this, but only when it is not visited, right? So that's why I need to maintain one array which is visited, right? Okay. If it is not visited, see what I'm saying here, that if you write only like this, okay, let's suppose, then what is the problem with this? Suppose, let me just copy it and let's just go to the next page. See what I'm saying, that if you don't write the visited array, then what is the problem? that if the node is visited, then you should not call the DFS, right? So that's why I'm just maintaining one thing which is visited. Okay, so this is a little modification. Okay, little modification. Okay, this is a little modification. Understood? So basically, if that is initially whenever I'm going to this, I'm saying this visited is true. Okay, and then if it is not visited, then only I will go to this. Okay, but that is the possible that from this particular U, okay, if I'm calling DFS on U, from this U, everything might not be visited, right? Which means everything cannot be traversed. So which means that from this U, you might not be able to reach to W. So will this algorithm work? Or there is some little modification that is required here. See, if we are calling on this particular graph, if you are calling, let me just paste it there only. Okay. So on this particular graph, if you are calling this DFS widget or DFS whatever this is, then will this work? Tell me. If you are starting at node U, no, right? Because you will be calling its neighbors and all, right? So there won't be anyone who will be calling this. There won't be anyone who will be calling this. So who is calling this? No one. In this particular implementation, no one. So we need to do a little more modification. So what we can do? We can say let's have one more function. Okay. This is just initialization of visited. Here I am saying that it will check for each vertex. So basically, it will call this DFS U. Okay. After this, if something is unvisited, then it will check. If something is unvisited, it will call the DFS again. Understood? If something is unvisited, it will call the DFS again. So that's how it will work. Anyway, so what is the time complexity of DFS? How much time it will be taking? See, what you are doing, you are just traversing for every node. You are just saying, okay, if this is false, then you are basically, if it is not visited, then you are doing this DFS. So for every node, how much work you are doing? Let's suppose this is V1, this is V2. Let's suppose this is Vn. Okay, for every node, how much work you are doing? At most, you will be calling its neighbors, isn't it? You will go to this vertex, and then you will just calling the neighbors. Neighbors one by one, which means you will call this you will call V, and then V will call its neighbor, and then let's suppose everything is done. Then you will call the second neighbor, which is X, right? If everything is done. So basically, you are just calling two functions here. At this point in time, you are just saying, okay, this and this. So you will say you are just doing for everything. You are just doing 1 plus. This is just constant work. You can say degree of V, because degree of V1. You are just doing the neighbors work. Okay. And if the degree is 0, then at least the constant work you are doing. So 1 plus degree of V1. Okay. So that much you are doing. If that is adjacency list. So you can say you are doing 1 plus degree of V1 if that is adjacency list. So what is the time complexity here? Let me write it. Okay, let me write it a little more clearly. What is the time complexity? See, you are just going to the neighbors. Okay, so that's why it is, if you are doing adjacency list, then 1 plus degree of V1, 1 plus degree of V2, like this. If there is an adjacency matrix, then in how much time you will be finding the neighbor? In how much time? Then in that case you will say it will be V. Okay, you will be taking V time. Here also V time, here also V time, all the vertices, right? So if there are total V vertices, okay, or the n vertices of V vertices, then in case of adjacency matrix, it is adjacency matrix. The time complexity is V square. Okay, V square. In case of adjacency list, how much is total this? This is, you can say, this is adjacency list. This is total. These are the V vertices. So 1, 1, 1, 1 V plus. And if you sum up all the degrees, then it will be 2E or E, right? So V plus E. Here V plus E. Here this is V square. So what is the time complexity of DFS? So you can say time complexity of DFS, right? So what are the time complexity of DFS? Can you tell me? Just let me know. In case of adjacencies list, what is the time complexity? In case of adjacency matrix, what is the time complexity? Just let me know. Yeah, okay. Okay. So I hope everyone got right? Yes, it is V. It is in case of adjacency list. If it is a list, then V plus E. If it is matrix, then V square. Okay. Great. Now let's just solve this question. This question I have taken from Princeton University. So what they are trying to say, let's just solve this question. Suppose that during an execution of DFS, okay, in a directed graph or digraph, it is also called directed graph, DFS V is called a recursive subcall after DFS W is called. So they basically they are saying that DFS W DFS V is called after W. Okay, I mean W has been called, and after some point in time DFS V is called. But before DFS W returns, which of the following must be true? Okay, so they are saying that DFS W is called, and after that, after some point in time, DFS V is called, which means what can you say? That this V must be reachable from W, right? See, if they are saying that you are calling, okay, let me just go to the next page and let me try to explain this. If they are saying this, that you are calling DFS of W, and after that you are calling DFS of V, what does this mean? Can I not say before it returns, which means in the graph, this is, let's suppose W, then W might be going to somewhere, okay, might be going to somewhere, but ultimately W is going to V. There is a path, right? There just exists a path, isn't it? See, let's suppose I say this, okay, in this particular graph, let's just take this particular graph, okay, or maybe there are many other graphs, so I can take this graph. So let's just take this graph. Now here if I'm calling this S, and after that let's suppose after some point in time I'm calling G, isn't it that I'm basically saying that S and G are connected? I mean there's a path from S to G, isn't it true? This is true, right? Now suppose I'm calling this, okay, I'm calling this D. See here, okay, see you can see using the times also, that which one I'm calling first and which one I'm calling later, right? You can see using the times also. So here, see, now in this question they are saying that you are calling some vertex, right? Some vertex. Let's suppose when are you calling this D? When are you calling this D? At time 3, right? Okay, you are calling DFS on some vertex D, and after some point in time, let's suppose you are calling DFS on G. Okay, DFS on G. Okay, so this is basically 4 5. I think that has not been copied, but it is 4 5, right? Okay, let's suppose you are calling DFS on G. Now you only tell me that if you are calling DFS on G, then what does this mean? Before you finish this DFS on D, see, you are calling DFS on D, and after some point in time you are calling DFS on G, then it must mean that there is a path, right? There is a path. Then there exists a directed path from W to V. From V to W you might not know. From W to V, that is for sure, right? From W to V. So that's why what is the answer? What is the answer here? B, right? B. There does not exist a path from V to W. You don't know. From V to W, you actually don't know. Maybe there exist, right? How would you know? There exists a directed cycle. Cycle also you don't know, right? I mean, you don't know. You don't know that there's a cycle or not, right? Containing V and W. You don't know this. May not be. I mean, it may not be, right? May not be. May not be. Okay. Now let's just modify this question little bit. Okay, let's just modify this question little bit, and I want you to understand only one thing which is important here. See here that let's just modify this question little bit. Let's suppose they say, okay, let's suppose they say this, which means they do not tell you whether the DFS on W may be returned or may not be returned. See, in the earlier question they are saying, but before DFS of W returns, okay. Now suppose they say that that DFS of W you call, and then after some point in time DFS of V you call, but you don't know at this point in time maybe DFS of W is returned or not, right? You don't know. In that case, what is the answer? In that case, what is the answer? See, my question here is that if you know, see, if you are calling, if let's suppose this is W, and then this W is basically going, and then it is calling this V, okay, after some point in time, where the W is not yet returned, then you can say there's a path. But let's suppose you are saying you're calling, and then there is in fact, okay, the W, let's suppose this is written, okay, let's suppose this DFS of W is written, and in fact there is a different component which is like this, okay, which is like this. This is V. Can you say there is a path from W to V? Can you say there is a path from W to V? No, right? In this case you can't say. See, in this case, before you are calling this V, at that point in time this W has already been returned. If W is returned, then you don't know basically there's a path between W to V or there's a no path, right? So actually we will formalize this using, okay, we will simplify these things using one theorem, okay, which is very interesting, very nice. Can anyone tell me what is that name? Can anyone tell me the theorem name? Can you write it in the chat box? What is the theorem name which can relate all of this, which is called DFS Parenthesis Theorem, okay? It is given in Corman. We will see this theorem, okay? Let's just see, okay? We will see this theorem, don't worry. Okay, but before that, let's just solve this question. This question has been asked in GATE 2014. What they are saying, that suppose DFS is executed on the graph and starting from unknown vertex. Suppose that recursive call to visit the vertex is made only after the first checking the vertex has not been visited earlier. Okay, then the maximum possible recursion depth. Okay, if you're calling, then what is the maximum possible recursion depth that is possible here? Okay, that's just a aptitude kind of question. So you can maybe start from here and then 1, 2, 3, 4, 5, 6, right? And maybe 7, 8, 9, 10, 11, 12, 13. Is the 13 answer here? So that's just an aptitude kind of question. Just see that what is the maximum possible depth that you can get. Tell me, is this better to analyze from here? Is it better to analyze from here? There is something called cut vertex. Okay, if you see from here, then it is not a good idea. I will tell you why. Because it is a cut vertex. Cut vertex will not lead to the maximum. Okay, I will tell you why. Because see, because if it is a cut vertex, then you will visit this, all of this, right? I mean, let's suppose this is A. Okay, let's suppose this is A. Then you will say A, and then you will, let's suppose, go to all of this. Okay, all of this. Okay, whatever this is, right? and then you will be writing this as a different subtree. Okay, you will be writing this as a different subtree. I mean, it will not lead to the maximum. You will not be continuing on the one branch. Okay, if you're starting from the cut vertex. Okay, the cut vertex is not a good idea to start with. So definitely there is a good idea to start with either this end or this end. Okay, so what is the answer here? Let me know what is the answer you are getting. So it seems like 19 is the answer. Okay, great. Total 21 nodes are here. 2 nodes requires the backtrack in this question. So what you can do, you can probably go like this. Okay, great. So you can go like this, right? In the zigzag fashion. So just an aptitude kind of question. Just aptitude kind of question. Okay. I hope you understood. Cool. So here, these two nodes basically, if you go, I mean, if you start from here, maybe then at this node you can say there's a backtrack is required, right? Or maybe like, let's suppose that if you're starting, I mean, if you're going like this, then you can go here and then you will backtrack. So basically you will be taking either this or this in this particular journey, right? So it's just like aptitude kind of question. There is no formulation or something that we can do here. Okay, but I hope you understood this. Cool. Now let's just see this. What this question is saying. This is GATE 2014 question. This is saying G be a graph with n vertices, m edges. What is the tightest bound on the running time? If you are using adjacency matrix. If you are using adjacency matrix, then what is the tightest bound? If n is the number of vertices, m is the number of edges. So I think n square, right? N square. If you are using adjacency matrix, then in case of matrix, theta of n square. In case of list, if it is list, then m plus n or v plus e. Okay. Cool. Now you can perform DFS using stack also, which means you can, let's suppose you are starting from here, then you will be writing A in the stack. Okay, you will writing A in the stack, and then you pop out this A and push all of its neighbors, which means B, E, and D. Okay, so maybe you can put B, D, and E. Put all of its neighbors. Then you pop out one of the neighbor. Okay, you pop out something. Let's suppose you pop out E. Then put all of its neighbors. Maybe you can put E and H. Okay, or okay. Let me write like this. See, you write this A. You pop out this A and then push all the neighbors. So what are the neighbors? So E, D, B. These are the neighbors, right? So you write all the neighbors here, and then A is visited. Then you pop out this B. You pop out this B, and then you put all of its neighbors. So what are the neighbors here? D and E are already done. So C is the only neighbor, right? Which is not done. Okay. Then this B is done. Then you pick this C and you pop out it, and then push all sorts of neighbors. So F is the only neighbor here. You pop out this F. There is no neighbor. Now you pop out this D. Push all of its neighbors. So G is the neighbor here. Okay. You pop out this G, put all of its neighbors. So H is the neighbor here. Okay, you pop out this G, H is the neighbor here. You pop out this H, put all of its neighbor. So I is neighbor. You pop out this I, there is no neighbor. Now you pop out this E, right? So basically, final answer is this. I mean, you can use the stack also to do the DFS. Okay. I hope you already know this. I'm just quickly telling you. Okay, this is a quick summary that you people might be knowing. Let me know if you have understood this. Okay, great. Now let's just go to the next thing, which is a very important theorem. It is called DFS Parenthesis Theorem. So let's just get started with the interesting things. Okay. So now we will see the interesting things. So to start with, there is a very first theorem that we will see, which is DFS Parenthesis Theorem. Very interesting. Nice, important, and interesting. Okay, let's just see what is this theorem. This says that let's suppose that you have some graph. Maybe let's suppose you have this as a graph. Let me go to the next page. Okay, let's suppose you have this as a graph, and what you want to do, you want to basically here you want to do the DFS traversal, right? Now see, let's suppose you are starting from A. Now let's suppose you are starting from A. Okay, for depth we need to count the number of edges or nodes. You need to count number of nodes. Okay, nodes only. I mean that A is one node, and then from A to B this is two node. So basically the in the stack you will put in the nodes, DFS of A, DFS of V, like that, right? So basically for that question, if you are asking, for that gate question, if you are asking, you need to count the number of nodes. Okay, so which means if you are asking for this question, then you need to count number of nodes. Okay, depth means nodes. Okay, now this A is there. Now what you will do, you will go to A to B, then probably you are going from B to C, like this, right? So for given this graph, you can write the finish time and the start times, right? So maybe we have already done this. So let me just copy paste it. Okay, so these are the finish time and start times that we have already done. Okay, now I want to tell you something from here. Okay, I want to tell you something from here. Let's just see that what I want to convey. Okay, so see, these are the start and finish times, right? Now can you also draw the DFS tree? Can you also draw the DFS tree? And then we will see what is this DFS parenthesis theorem, which is very nice and interesting also. Can you also draw the DFS tree? You will say yes. From A, you have gone to B, right? From A, you have gone to B, because this is 1, then this is 2. Then from the B, you have gone to C. And then what is 4? 4 is done. And then what is 5? You have backtracked this. Then you have from this B, you have gone to D, right? You have B, from this, you have gone to D. And then from this D, you have gone to F. Then F is done. From this D, you have also gone to E. From this D, you have also gone to, first you have gone to F, and then you have gone to E. Okay. And I, A, B, C, D, E, F. I think everything is done, right? So this is called DFS tree. This is called DFS tree. Now, one thing is to note here is that how to go. I mean, if this is given to you, then how to go from here to here? Which means that if someone asks you, okay, let's suppose there's a question. The question is that given this particular discovery time and the end times also, discovery time and the finish times, draw the DFS tree. If that is the question, then how you will solve it? Okay, so from here to here, how to go? I mean, one way is that, okay, this is 1, this is 2, this is 3. Okay, I mean, you can traverse back, you can use your intuition. One way is that. But there is very nice theorem which can relate these two. Okay, the question, I hope you understood the question. What is the question? Given the graph with the with discovery and finish times, draw depth first tree. Okay, suppose this tree is not given to you, then how you will draw? Can anyone tell me how you will draw? Now what you will say, that, okay, this A is here. From this, because this is 1, you might have gone to 2, I mean this B, then this is C, then 4, then you must have backtracked, and then this is from this B, where is 5? This is D, right? So from this B, you might have gone like this, right? There is one way, this. The other way is called parenthesis theorem. Okay, so we can make use of parenthesis theorem to do this. We can make use of parenthesis theorem here. Okay, let's just see how we can make use of parenthesis theorem. Now, what is the time of A? Can anyone tell me can anyone in the chat box write me the time of A? both the times 1/12, which means at 1 it has been started, at 1 it has been started, at 12 it was finished, right? So this is 1 to 12, okay, which is A. Let me know if that is okay to everyone. Okay, this is A, 1 to 12. Now what is the time of B? This is 2 to 11. So this is B, right? This is 2 to 11. This is B. Okay, what is the time of C? It is 3 to 4 only. So maybe you can write here, this is 3 to 4. This is C, which is 3 to 4. Okay. Now what is the time of D? It is 5 to 10. So D is basically, you can say it is 5 to 10, right? Okay, I mean, I'm writing with respect to time. This is 1, 2, 3. I'm writing in the increasing order, which means, I mean, this is a timeline, right? This is a timeline. So this is 1, then this is 2, then this is 3, this is 4, 5, 5 to 10. What is the time of maybe F, which is 6 to 7? Okay, so you can write it F here. 6 to 7. What is the time of E? It is 8 to 9. So E is 8 to 9. Okay, let me know if you can draw something like this. If you can draw, given this, so let me just little minimize this. Okay, given this, can you draw something like this? Let me know. Is this okay to everyone, that how to draw something like this? Okay, so see, this is 1 to 12, and that's why I made it big line. Okay, and then B, and which is 2 to 11, and so on. Now, as you know, this A is covering all, right? So which means A is a parent of all. From A, there is a B. Then B is having two children, which is C and D. Okay, which is C and D. Then C doesn't have any children. Then D is having the children, because this was 6, right? This was 6, so that's why I have started from here. D is having a children, which is F and E. F and E. Can you not draw something like this? Okay, see, very easily, if this is given, this particular thing is given, then using the parenthesis theorem, can you not draw this particular tree? Let me know. Let me know if you can draw. Okay, just tell me in the comment box if you can draw. See, what you need to do, see, this was the question, that we need to draw the tree, right? This was the question to us. What I said, like, you can make use of something called as parenthesis theorem, right? You can make use of something called as parenthesis theorem. So it says that you are basically making a parenthesis, which means this is a parenthesis of A, okay, which is, let's suppose I'm labeling it at A. This is a parenthesis of B, this is a parenthesis of C, this is a parenthesis of D, this is a parenthesis of F, this is a parenthesis of E. Okay, so this is a balanced pair parenthesis, which means interestingly, if this is a parenthesis of A, let's suppose, in between, okay, this is a parenthesis of A. In between, if B has started, which means if this is a parenthesis of B, then B must have ended here only, which means before A it must end. Okay, before A it must end. See, GATE also has asked many questions regarding this. Okay, just regarding this concept. What I'm saying, if B is starting after A, okay, B is starting after A, then because of the balanced pair parenthesis, B must end before A only. Okay, B must end before A. Okay, which means I will, don't worry, I will make it extremely clear. Okay, first I'm just making the parenthesis, which means this will say that if C is starting here, this is C is ending here, and then D has started here and here, this is D, right? And F has started in between, this is F, and then E also has started in between, this is E. Okay, so these are the parentheses corresponding to this. This is balanced pair. Balanced pair means that it is not the case that if B is starting here, B can't close here. It's not the case. See, what is the balanced pair parenthesis? You might be knowing it, right? Tell me, is this the balanced pair parenthesis? Is this the balanced pair parenthesis? Yes, right? This is balanced pair. Tell me, is this balanced? This is balanced. Right? Tell me, is this also balanced? Is this balanced? Not balanced, right? Not balanced. So just see here that this is balanced, but this is not balanced, because if this is starting, this is ending, in between this should be balanced only, right? In between this should be balanced only. So since this is not balanced, so that is why it is ultimately not balanced, right? So similarly, if age started here, age ending here, and in between if the parenthesis of B is there, then that's okay. We can put the parenthesis of B. Then it should be start and end both. Okay. It cannot be just start or cannot be just end. That's called balanced pair parenthesis. See this particular diagram. That if S is starting here and after that if Z is starting, that is okay. Okay, if Z is starting, this is the particular diagram that I have taken from Coreman. This is diagram from Coreman. It is saying if S is starting here, see the parenthesis of S, then in between if Z is starting, that's okay, but it must end also. Okay, before S only. That's called balanced pair parenthesis. Now why this theorem is so important to solve gate questions? I will tell you. Okay, there are many questions they have asked just based on this theorem. See, if S has started and after that if Z is there, then it can't be the case that, okay, can it be the case? See, tell me, can it be the case? S is starting, okay, S is starting. After that, let's suppose Z is starting. Can it be the case that S is finished and Z is not yet finished? Is it possible? Tell me, is this kind of parenthesis possible? Is this possible? Answer is no, right? Answer is no. And Gate has asked many questions regarding this also. I will tell you how. See, let's just understand this intuitively also. Let's suppose this is S. And you are starting S, and after that, after some point in time, you are saying, okay, there is a Z that you have discovered. Now you start this Z. Okay, you start this Z, which means Z will go, keep on searching and so on, right? And then maybe backtrack, and Z is finished, right? Okay. So which means you are starting S, you are starting start of S. You are starting S, and then in between maybe you can start Z, and then you must be finishing Z. You must be finishing Z before you finish S, right? Before you finish S. I hope that is clear. And why that is the case, we will see using the graph also. Okay, finish. Is this okay to everyone? If you're starting S, after that you are basically starting Z, then you must finish Z, okay, in between only. It can't be the case that Z will be finished later. And that is obvious also. Why that is obvious? See here, if you're starting S and after that you are starting Z, which means first of all, there's a edge between, there's a path between S to Z, right? We have seen one question regarding this. And then after that you are saying that, okay, let me go searching and then maybe backtrack, and then obviously you must be finishing this Z first, right? Then only you will be backtracking. See, backtrack and finish is same. Backtrack, whenever you are backtracking, it means you must have finished on that node, right? You must have finished on that node. So you must backtrack to go back to S, right? You must backtrack to go back to S. Since you must backtrack, which means you must finish on this Z. Obviously, right? Obviously. So if that is the case, then after starting S, if you are starting Z, then basically you need to finish this Z only. Okay, you need to finish this Z. So basically this is called balanced pair parenthesis. Okay. Now obviously if I give you something like this, then definitely you can draw the tree, right? Or maybe you can see the tree. Drawing tree is just one thing of this parenthesis theorem. That's not the only benefit of parenthesis theorem. There are many benefits, I will tell you, okay, of this parenthesis theorem. Now you just tell me, let's suppose I ask you this. Suppose this is a question. Suppose there is a graph where S is connected, is having directed edge from U and V. Then if we start S first, then what can you say about UB as finish times? Okay, which means they are saying there's a directed edge. Okay, there's a directed edge from S to U and S to B, which means there's a directed edge from S to U and from S to B, and they don't know whether UB having any edge or not. So if you're starting on S, then what can you say? Can you say that finish time of S, okay, must be greater than finish time of U? Can you say this? Will this always be true? See what I'm saying. Let's suppose this is S. They are saying there is a directed edge from S to U and there is a directed edge from S to B, and you are starting on S first, okay, and everything else is not given. Let's not worry about it. Okay, you are starting this S first. Now which is true? Okay, which is true? Finish times of S, finish time of S is always greater, which means S will finish later than U. Is this true? Finish time of S is also greater than finish time of V. Will this true? Finish time of U is greater than finish time of V. Will this true? Okay, or maybe finish time of, or maybe you can say start time. Okay, that's going to be the interesting question. Start time of U, okay, or we also call it discovery time. So let me write it D. Discovery time of U is greater than discovery time of V. Let's suppose this is MSQ for this particular graph, which is always true. Okay, which is always true? Tell me, which is always true for this particular graph? Can you tell me? Just think about this question. This is a good question. See, they are saying that we have started on S. Okay, we have started on S. On S. Suppose this is given to us. We have started on S. Just think about it. Let's suppose this is A, B, C, D. See, you have started on S. Now, obviously you will be either going to U or V or something. I mean, since there's a path, right? There's a path. You can't just backtrack, and you can't just finish this S before finishing either U or V, because there's a path. So either you will be going to U first or you will be going to V first. Which one you will be going to first? Do you know? Do you really know the discovery time, whether you will be going to U first or V first? Anything, right? Maybe U first or maybe V first. So basically you are starting this first or this first. I mean, you don't know, right? Since you don't know, so maybe you can start U. Okay, you can start U. This is S. You can start U, or maybe someone can say, can I start V? Yes, you can start V. See, I don't have any problem in that. You can start with U or you can start with V. Which means this discovery times, you can't say whether U's discovery time is greater or V discovery. You don't know, right? This is not always true. So that's why this is false. This is definitely false. Because about the discovery time, can you say about the discovery time? No. You can't say whether U will be starting first or V will be getting starting first. So about the discovery time, we can't say, right? But can we say about the finish times? See, let's just see if we can say about the finish times of S and this. Let's just see. See, can I say about the finish time of S if we are starting this S and after that I will be starting U. If there's an edge between U to B, then maybe I can start V here only, which means U, and then V here only. This is one possibility. If there is no edge, okay, if there is no edge, which means let's suppose there is no edge between U to B, then after starting U, I will say if there is no path from U to B, then maybe it can be finished, and then I will be starting V, right? Either this is possible or this is possible. If there is an edge, then this is possible. If there is no edge, then this is also possible, right? So basically, one thing is for sure that this finish time of S is here, and before this finish time, everyone, which means U and V, must be finished. Because you will be starting them anyway, right? You have to start them because S, this U and V are reachable from S. Since they're reachable from S, you must start U and V. After starting S, you must start U and V. Hence, you can say that finish time of S will be definitely greater than U, than V. What is the finish time of U and V? You don't know. You don't know the relationship between U and V, right? You don't know. Maybe U is getting finished first, and maybe V is getting finished first. You don't know. I mean, if you're choosing to go to V first, then maybe the discovery and finish both are it first. And if you're choosing to go to U first, maybe you start first, finish also first. Okay, you don't know basically, right? So that's why A and B are true. C and D are not always true. Understood? Okay, so this parenthesis theorem is extremely important. You will get to understand why. Okay, you will get to understand why. See, this is the parenthesis theorem that I have taken from Corman. Now, what this is saying, this is saying that for any U and B, exactly one of the, okay, so this is saying that either this is true, which means for any U and B, either this will happen or this will happen. Okay, or this will happen. For any U and B, they are saying only three possibilities are there. This is V, this is U. Okay, I mean they are very independent. I mean this U start and V start independently, which means U start and you don't see V, right? You don't see V. Maybe V you will see later on, right? That is not reachable from U. You will see V later on. Then you can start this V later on also, right? If that is not reachable. So either this will happen, that U and V are like this. Either this will happen or this will happen. What do these mean? Let me just tell you. See, what do these mean? This is basically from Corman. They have written three cases. I am just translating these three cases, whatever they have written, I am just translating that into the diagram. Okay. So what does this mean? Can you tell me? As a tree, what does this mean? They are saying that either U is a parent of B. Okay. Either U is a parent of B, parent or ancestor, whatever you want to call. Either this is the second case. The third case is that, or maybe V. See, here this B is a parent or the ancestor of U. Right? Either V is a parent or the ancestor, or U is an ancestor. Or maybe something like this, that they may be under S, right? They may be under some S, or maybe they're independent, doesn't matter. So maybe there is no relation, maybe like this, right? U and V, they're independent, which means neither U is an ancestor nor V is an ancestor, right? Something like this. Understood? So they are saying there are only three cases that can happen. Let me know if that is understood. If that is understood, then basically you can visualize. Okay, if you see this particular, if that is visible to you, let me little bit make it smaller. Okay, so what they are saying, that you can visualize this particular interval like this. So basically you can say, earlier we were writing like this, now we will see as a bar. We will say, okay, we will visualize like this, right? Okay, now let's just solve this question. This question has been asked in GATE 2006. What they are saying, consider the depth first search of undirected graph with three vertices PQR, and the discovery times are also given. U is visited first, and then okay, discovery time and finish time is given. So they are saying that P discovery time and P finish time are like this. So which means P, this is P, 5 and 12. This is P. Q is basically 6 and 10. Q is 6 and 10. This is Q. R is 14 and 12, 14 and 18. So basically they are saying this is PQ and R is something like this. 14 means here. Okay, R is 14 and 18. Now they are saying that which of the following is true about this graph? Can you make the DFT using this? Using this information, can you make the DFT? See, we have just write it in the parenthesis way. Okay, now can you make the DFT? Let me know. See here that this is P, then you will say that from P to Q, this is a relation and R is independent. So what can you say here? There is only one connected component. This is undirected graph. There is only one connected component. See, the tree will be directed, okay? The tree will be directed, but the graph, original graph could have been this, okay? In the tree there is a direction, but in the graph there is no direction, okay? And a tree will always be directed here in our case, right? So the DFS tree or the BFS tree, that's called rooted tree, okay? Rooted tree. These trees are having the direction, which means the direction from root to the descendant, okay? And from this particular node, to this. So we will be having the directions in the tree, that's okay, but there is no direction in the graph. So the graph is like this. So what is the answer? There is two connected component and PQ are connected. Yes, and P and Q are connected. So this is how the graph will look like. Okay. See, using parenthesis theorem, can't you solve this very easily? Using parenthesis theorem? Let me know. See, if you don't know the parenthesis theorem, then it will be little tricky. But if you know the parenthesis theorem, then you can definitely solve them, these kind of questions very, very easily. So that's why this parenthesis theorem comes very handy. We will see many other questions. Don't worry. We will see many other questions of this parenthesis theorem. Okay. Cool. First, let me know if that is okay to everyone. Okay. Okay. Now let's just go to the next question. Okay. See this question. This question has been asking GATE 2007. This is quite interesting question. What they are saying, the DFS is performed on a directed graph. DU represent the discovery time. Okay, if you represent the, okay, that's fine. Which of the following is always true about all edges UV? So let's suppose there is an edge UV in the directed graph. Okay, this is directed acyclic graph. Interestingly, this is directed acyclic graph. Okay. Now here they are saying, let's suppose this is U, this is V, this is V. They are saying for any edge UV, okay, what is true? What is true? I mean, they have not given the complete graph. Maybe this is S, which might be connected to U, which might be connected to B also, right? I mean, you don't know. Basically, let's suppose this, right? You don't know. Okay. So if this, they're just asking about this edge. See, this is a acyclic graph in the sense that tell me if this is the edge from U to B, can there be a path from V to U? If this is acyclic, can there be a path from V to U? If there's an edge from U to B in the acyclic graph, in the directed acyclic graph, then can you have any path from U to B? V to U? No, right? You can't have. Okay, that's for sure. You can't have any path from here to here. Why that is important? I will tell you. See, now they're asking, let's suppose this is S. Okay, you don't know the other things, but let's suppose this is something like the graph look like. Okay. They're asking about that which can you always claim about the finish times and the start times. See here. First tell me, can you claim anything about the start time? That you are starting U first or V first? You can choose. See, if there's any edges given to you, I mean, if there is for any edge, it depends. Maybe let's suppose there is some vertex S is connected to both of them, right? Let's suppose this S is connected to both of them. Maybe you can choose U first. Maybe you can choose V first. Can you claim anything about the starting time? That starting time will always be lesser or greater? See, can you claim anything about the starting time? Tell me. The answer is no. We cannot claim anything about the starting time, right? So the start time claim cannot be there. Why? Maybe you can choose U first. Maybe the graph is like this. So for this edge, maybe this you can choose U first. Maybe you can choose V first, right? It is basically not clear that which one we will be choosing always. So see here, maybe you can choose V first or you can choose U first. So the starting time we can't say. Now you tell me just one thing. Suppose you are starting this U. Okay, let's suppose this is U. Okay, this is start. I mean, this is basically some time. I'm not writing time, maybe 1 to 10 or something. Okay, which means you are starting this U and you are ending this U here. Tell me, will you not start this V first? I mean, there are two cases. Either you will starting U and V, right? Let's suppose you are starting U first. Tell me, won't you be starting V? Won't you be starting V in between? Is this even possible that you can't start V in between? Which means if you are starting U first, okay. So let's suppose this is a case one where I'm starting U first. Is it even possible that you don't start V in the between? Maybe you start it later. Tell me. See, if it is reachable, then you must have to start. Okay, after starting this U, you must have to start this V if it is reachable. So this is not possible. Which means, see, what I'm trying to say here is that there are only two cases, right? What I'm trying to say, there are two cases. You start first or we start first. Okay, I mean the starting, obviously you can't claim that which one is getting started. If U is getting started first, then there is for sure, let's suppose this is getting started first, there is for sure that V must be here. Okay, you can't escape it because that is reachable. If it is reachable, then you have to start it, right? If it is reachable. Now if V is starting first, this is the case 2. Okay, this is, let's suppose, case 1. This is case 1 and this is, let's suppose, case 2. Okay, this is case 2 where V start first. If V is starting first, let's suppose this is V. Okay, sometimes are there, V is starting first. Will you be starting U? You be starting U in any way between? Tell me. Is there any path from V to U in this acyclic graph? In this acyclic graph, is there any path from V to U? Just tell me this. No, right? Okay. So you tell me, will you be starting U after that or not? Will you be starting U? No, right? You want to be starting U in the between. Then what will happen to you? You might be starting it later on, right? You might be starting it here. So basically you can say maybe you can start it later on, but you will not be starting in between. That is for sure, because there is no path actually. If there is a path, then I can start. Then I will start actually. Okay. If there is a path, then I will start. If there is no path, then that's the relation. So either this will happen or this will happen. Anyway, whatever is the case, you can say one thing. What you can say? That this U is finishing later, right? U is finishing later. So for the finish time, you can say that if that is the edge between U to B, then you can't finish this U and U before finishing this V, which means, see, in both the cases, this U is finishing later, here also U is finishing later. So about the finish time, you can say that finish time of U will be greater, right? Start time, you don't know. You will be starting U first. Sorry, you will be finishing V even before starting this U. So is this true? The finish time, no, right? In this case, it fails. Okay. So intuitively also we can understand. See, intuitively also, let's just understand this. Let's just try to understand intuitively that which option is true. Okay. See here, you only know about one edge, which is U to B. They are only asking about this edge. Okay. Now you see this. You see this here. Can you finish this U? Can you finish? See. One thing is that, can you tell me about the start time? Which start time is greater, U or B? So we cannot comment about the start time, right? We cannot say about start times. Okay. What we can say, but we can definitely comment on, we can definitely say about finish time. What we can say, see, you just tell me that start time we can't say, but you just tell me, can you not say directly intuitively also, can you not say that you can't finish this U before finishing this V? Can you say that, okay, I'm done, and you don't finish this? Can you say? Is this even possible? Can you say this U is done even before you finish this V? No, right? So that is why f of U, the finish time of U is always greater than the finish time of V. Okay, it is always. What about the start time, which means discovery times? What about the discovery times? You don't know, right? Don't know which one is greater or which one is lesser, but about the finish time you can always say this. Okay. So we cannot say anything about the start time. We can definitely say about the finish time. So what I'm saying, for any edge in directed acyclic graph, okay, if you have any edge which is, let's suppose, U to V, if you have any edge something like this, then what can you say? Always that is the case that you can't finish this U, right, before finishing this V. So the finish time of U will always be greater than always be greater than the finish time of V. Let me know if that is okay. Okay, if that is fine. So basically, let me just tell you something in little advance. Just a second. Okay. Yeah. So this is the screenshot from Stanford also. Okay. See here in a DAG we always have this. In a DAG we always have this. Right? This is also the Stanford says. If you see this is a screenshot from Stanford. Okay. In a DAG for everything, for any edge, we always have this finish time larger. Obviously you will be finishing it later on. Okay. You will be finishing this first, you will be finishing this later on. Cool. Does this give you some idea about something called as topological sort? Okay, we will talk about it. So basically from here, actually we can drive something called as topological sort in the DAG. See, as you always know that this finish time is greater, right? This finish time is greater than this. If there is an edge like this, then you will say that what we can do, we can take the greatest finish time, right? Whoever is finishing last is actually the first node in the topological sort, and the next node and the next node. So we will talk about this topological sort, but basically just this kind of relation, that finish time of A is greater than the finish time of B. Just based on this observation, we can do something called as topological sort. Okay, we can do something called as topological sort. I will tell this later on. Okay, in the applications I will tell you. Cool. Let's just solve this question first. This question has been asked in UGC NET in 2015. What they are saying in the following graph, discovery time is time and the finish time is time of the depth first search is like this. Okay, this is discovery time / finish time. Okay, now they are saying which of the following is the DFS tree. Can you make the forest out of it? Maybe, right? So maybe you can start from C. You're going to start from C. Either you can use a parenthesis theorem or you can use just an intuition that from the C you are going to G, right? And then which is 3, 3 is F, so you are going to F, right? And which is 4, now you need to backtrack, which means you will go to G itself, and from this G what you are doing, which is 5, you are going to H, right? Which is 6 is this only, so you need to backtrack, which is 7, so you need to backtrack at 7, which means you are at G now, right? You are backtracking, which means you are C, so which is 8, you are going to D, basically C to D, right? And then this is 9 itself, so which means you are backtracking, you are again back to C, you are backtracking at C, which means that is done, right? That is done. So which is 11, now you will be having B as separate. Okay, B as separate. Okay, and then which is 12, then you are having E, right? Which is 13, then A, then this is 14, you will go here, 15, I think this E is done. Okay, and then E, from E you will go to B, and I think everything is done, right? So A, B, C, D. So basically what is the answer? B, A, B, E, A, B, E and C, D. Yeah, so I think A is the answer, right? A is the answer. Okay, cool. If you want, you can use a parenthesis theorem. Okay, I mean maybe you can do something like this, which is using the parenthesis theorem, that okay, this is C from 1 to 10 and then this, but that's okay if you directly do it also. Okay, now this question is interesting. They are saying that given this again, this finish time and the discovery time, they have not given the graph, they have only given the finish time, discovery time. Okay, finish time and the start time. What are the descendant and ancestor of V6 and something they have asked, right? So let's just solve this question. So this question I have taken from some university. Let's just quickly try solving it. Okay, let's just quickly try solving it. So what they're saying, that at 1, 7 is starting. So maybe you can say this is from I think, okay, so 10 is not highest one. Okay. So from 1 to 10, this is V7. Okay, and then what is 2, 6, V6, right? So this is V6. Okay, Then what is 3? This is basically 2 to 9. Then 3 to 6 is V5. V5, this is 3 to 6. And then what is 4 here? Where is 4? Okay, V1 is 4 to 5. So this is V1. Okay. And then what else? I think after 6, 7 to 8, this is V2. Okay, this is V2. And 8 is okay. 9 is there in 9? Okay, 9, 10 is also done. Okay, so this is V2. Cool. And then you have I think from 11 to 16 there is something else. Okay, from 11 to 16 you have V8, and then from 12 to 13 you have V3, and then 14 to 15 you have V4. 14 to 15, I think that's done, right? You have V4. So basically you can make the tree, which means V7, from V7 you are going to V6 only, right? V6 only. This V6 is going to V5 first, and then this is going to V1, and then this is going to V2, right? V6 is going to V5 and V2. Here this V8 is going to V3 and V4. Okay, so basically given this data, you can definitely make a tree. Once you make a tree, you can do all of this question. What are the descendant and ancestor of V6? Okay, you can see what are the descendant and ancestor. So descendant in V5 and V2, and ancestor is V7, right? So you can solve all of this. Okay, I mean the answers are here on the next page. Okay, so yeah, so the ancestor is V7, the descendant nodes are 1 to 5. So basically this 1, 2 and 5 all are the descendants. So you can answer all of this once you make this tree. Okay, so whatever they have asked, once you make the tree, you can definitely answer all of this, right? Okay, can you do this question also as an homework? This is from CMI. Entry means like start. Okay, start, and exit means finish. Okay, so they are saying given the following data DFS, construct the DFS tree. Okay, I think answer is on the next page. This is the solution, but just try this as an homework. Okay, just try this as an homework. This question is from CMI, which is Chennai Mathematical Institute. This question is from CMI. Okay, let's just see this question. What they are saying, this is interesting. They are saying this is true or false. If V and U are not equal, V is descendant of U, which means V is here and U is here in DFS tree, which means there is a path from U to B in the tree. Okay, if and only if this is true or false, S means start, that you are starting U, you are ending. Okay, this is U start, I mean this is U, this is V. If and only if this happens, is this true or false? They are saying that if and only if this happens, then only, which means this kind of diagram, then only that U and B are basically ancestor and descendant. I mean U is ancestor. Is this true or false? Let me know. As per the balance parenthesis theorem, you know this is true, right? This is true. There is, I mean, if that is the case, then obviously that's the thing, and or vice versa. If that's the thing, then that will be the case. So basically, this is true. Okay. Yes. So you can say the answer here is true. Now tell me which of the following is not possible. Okay, which of the following is not possible? That this is start. D means start. Okay, or F means finish. That you are starting U, you are finishing U here. Okay, this is U. In between you can start V. This is definitely possible, right? I mean that is using the parenthesis theorem. You can say this is possible. Is this possible? That you are starting U, finishing U, then starting and finishing? Yeah, that is also possible. Is this possible? You are starting and then you are starting V. Oh, see here. Is this possible? Is this possible? You are starting U, then you are starting, in between you are starting V, okay, and then you are saying, okay, let's just U is finished, which means you are saying let U is finished. Okay. Is this possible? Before finishing, and then we will be finishing here. U is like this and V is like this. Is this possible? Then answer is no. So since this is not possible, that's why this is the answer. Is this possible that you are starting V and then U, finishing U and V? Yeah, this is also possible, right? This is also possible. So basically this D is not possible. Oh, sorry, this C is not possible. Okay. Now let's just solve this question. What they're saying, suppose DFS of G is basically this, I mean the discovery time of some node and the finish time of some node is given, which is 30 and 50. Okay, which means at 30 it is starting, at 50 it is ending. This is V. Okay. Now what they're saying, suppose W is gray. Okay, basically let me just tell you what this terminology is. See, see, let's suppose there is some graph that we have. Okay. See, this is a terminology which is standard coloring, which is a Corman. I mean, the Corman has used this terminology at first, and then actually every author is using the same terminology. So let me just tell you that what is this terminology, this gray and all. Okay, maybe they ask you. I mean, they will define the terminology obviously, but if they ask you, then you should be a little familiar. Okay, so let me just take this graph and let me just tell you that what does this terminology mean. See here, that this. See this, once you start this A, okay, initially any vertex is visited or unvisited? Tell me. Visited is false for any vertex, right? So basically we are saying either the vertex is visited or the vertex is unvisited. I mean, maybe you visit it or maybe you don't visit it. I mean, initially it is unvisited, so initially it is unvisited. Basically visited is false. Now, just because there are some regions and there are some applications based on, I mean, using, I mean, due to which we need to divide this visited also in two parts. Okay, what are those two parts? I can say in stack or finished. Okay, which means, let's suppose I say this is A. Okay, A is going to B. Tell me this A is visited or not. If you are at B, this A is visited or not. A is visited, but A is in stack or it is finished. A is in stack, right? I mean, it is not yet finished. It is going to B. B is also visited. B is going to C. C is also visited. Now C is basically you will say it is backtrack and you will say C is finished. It is visited also, it is finished also, right? So if you are backtracking, then you will say it is finished. So in visited also there are two categories. Can I define two categories? In stack and finished. Okay, just because there are some applications, I mean, this DFS is having some applications. For the practical purpose, I'm just differentiating whether it is in stack or in finished. So here in the Corman, they have used the colors also. So basically, instead of saying in stack, finished, unvisited, they are saying 0, 1, 2. Okay, or maybe I think you can say this is in unvisited is 0, false. This is true. So maybe you can say it is 1, this is 2 or something like that. So they have used some numbers. Okay, I mean, one idea is that you can say in stack, finished, unvisited, or you can say 0, 1, 2. 0 means unvisited. Okay, you can maintain some array visited. Say earlier also we were maintaining that array. Earlier we were saying 0 or 1, true or false, right? But now they are saying 0, 1, 2, which means 0 means unvisited, 1 means in stack, 2 means it is visited, and finished. 1 means visited and in stack. Okay. So actually instead of 0, 1, 2 also they have some other terminology. I mean, many authors use that terminology. They say instead of saying 0, they say it is black. Okay. They say if it is finished, they say it is white. Okay. If it is in stack, they say it is gray. Okay. Gray means it is in stack, visited but in stack. Okay, anyway, that's just a term I'm introducing you. Why that is important? Maybe because for some application they need it. Okay, what kind of application we will talk about it. Okay, what kind of application we will talk about it. But maybe for some application they need it. Okay. So what does the gray means? Gray means it is visited but still not finished. Okay. So they are saying suppose W is gray. Gray means they have given some time for V. Okay. Now they are saying suppose W is gray. Gray means it is visited. It is visited but gray at 30, which means it is visited but not finished. So now maybe at this 30 it is visited. Okay, so which means the W must have been started here, and not finished means can I say that W is this? Okay, but since the W can't be this, so W has to be this, right? See what I'm saying, maybe I can just tell you. See what they are saying. They are saying that W is gray whenever you are first time visiting this, I mean at the discovery time, this V, the W is gray. Okay, gray means it has already been visited but not yet finished, right? So maybe you have visited it first but not yet finished. This is W. Now tell me, can I end this W before this V end? Can I say this is a possibility? Just let me know. If W has been started first and it is not yet I mean at this 30 not yet finished because it is gray, can I say it will finish like this? No, right? No, it will be finishing it. If you have to finish, it will be something like this, right? Now they are saying if W is gray at that time 30, what are the possible colors at time 50? So at 50, what is the situation of W? It is gray only, right? It is visited only, right? Visited but not yet finished. So it is gray only. So what are the possible colors? Which means it is visited but not finished. Okay. Suppose W is white, which means it is unvisited. Okay, if it is unvisited, then what are the possible colors? So basically if W is white, which means you will be visiting it later on, maybe, right? Maybe later on. So at the time of 50, what are the possible colors? This is interesting. Can anyone tell me? So maybe you will visit it here, or maybe you will visit it here, right? So if you're visiting it here, then at the time of 50, it is already done. So if it is done, you will say for the done, I think we are saying it. If what color we are using, I think for the finished we are saying white, right? Okay, I think the terminology is this. Anyway, this doesn't matter. So I think they call it white. If it is unvisited, here they call it black. Okay, if it is finished. So maybe let me ensure of that terminology, because they will define the terminology in the question itself. But what are the possible things that may happen to W? You can say it is either finished by the time of 50 or not yet visited, right? Not yet visited, even single time. I mean, what I mean, not has started basically. Okay. Maybe it is finished already. Maybe it is finished already by that time of 50. Maybe it is finished already, or maybe you can say it will start later on, right? Which means either it is finished or not yet visited. Okay, easy question only. Okay, so now let's just see DFS edge classifications. Okay, so there are different type of edges that DFS has. So let's just see those edges, that what kind of edges that DFS has. Okay, there are tree edges, back edges, forward edge, and cross edges, right? So there are tree, back, cross edge, back edge, and forward edge. In undirected, there is only tree and back edge. So we will see that what are these edges. Okay, so maybe I can have one example. Let's suppose this is the example. Let's suppose you are starting at A. Okay, if you are starting at A, maybe at A you can go to, from this A you can go to anywhere. You can go to B, you can go to C, you can go to D. So let's just suppose that you are going to anything. Okay, maybe you are going to B, and then from this B you are going to D, and then from this D you are going to, let's suppose, F, and then you will backtrack. Okay, this is F, and then you will backtrack to D. Are there other options? Yes, you can go to E, right? You can go to E. Then you will you will go to, okay, you will backtrack to D. Are there other options? No, right? I think A is done, B is done, D is done, E, F. Okay, at D there is no other option. You will backtrack at B. There is no other option. You will backtrack, I think, at A, right? So now from this A you will go to C. Anyway, this G and H will be separate, which means if you are starting at G, then it will be G and then H. Right? This is the forest that you will be getting. Okay, this is the forest that you will be getting. Is this okay to everyone? This is the forest that you will be getting. Now in the tree or in the forest, what are the edges here? These are called tree edges. Okay, whatever is the edges in the DFS tree, these are called tree edges. Tree edges. Okay. See, this is the tree edge, this is a tree edge, this is a tree edge. Whatever the edges in the DFS tree, which are called tree edges. Now, as you notice here, that there are many edges which I have not drawn because that is not the part of tree. For example, this, right? For example, this. So this edge I have not drawn. For example, E to A I have not drawn. Where is E? This E to A I have not drawn. This is one edge. So there are many edges I have not drawn. Those other edges has been classified into other parts. So for example, E to A I have not drawn. A to D, this edge also I have not drawn, right? A to D I have not drawn. Okay. So see, see, this edge is called back edge. What is this back edge? Back edge means in the tree, this is a tree, in a tree, whatever edge is going, I mean in a tree, see there is a tree edge only. Okay. In a tree, we only have tree edges, right? Now, if you try to just complete it, okay, if you just try to complete it, that's why I'm making the dots, okay, that's why the reason I'm making dots here, because if you just try to complete this graph, okay, I mean this tree, then whatever the edge which is going from descendant to the ancestor is called the back edge, okay. This is the back edge because this is going from descendant to ancestor. If some edge is going from ancestor to descendant, that is called forward edge. If some edge is basically having no relation, I mean this edge is you can't say that A is a descendant or G is a descendant, that is called cross edge. Okay. So for example, let's suppose this is the tree that I have made. Okay, let's suppose this is the tree that I have made. Okay, there are multiple possibilities, but let's suppose this is a tree. Now the dots I am making just to tell you that okay, these are the edges which are not in the tree. This solid edges are in the tree. Can you tell me this edge? This edge, what is the type of this edge? Can anyone tell me? This is a cross edge, right? Why? What is the reason? Because this is in between two nodes which is having no ancestor or descendant relationship. What kind of edge this is? This yellow edge, can anyone tell me what kind of edge this is? Since this is from descendant to ancestor, okay? See, in the tree that is not there, but in the graph that is there, right? In the graph that is there. So that is called which kind of edge? Back edge. If the edge is from ancestor, okay, from ancestor to descendant, see that edge is not in the tree, but in the graph that is there, right? But that is called forward edge. And if that is in the tree, then this is called tree edge. Okay. So see here, if I just put it there only, then you can just check, right? See this. Understood? Let me know if that is okay to everyone. Okay. So you understood that how to classify between tree edge, back edge, and these things, right? So see here, this edge is from ancestor to descendant. That's why it is forward edge and so on, right? Okay. Now here also, like there are multiple possible DFT for that graph. Here also, what kind of edge? Let's suppose if I just ask you that what kind of edge this is. Can you tell me what kind of edge this is? This is a back edge. This is a forward edge. This is a cross edge, right? This is a, yeah, can anyone tell me this edge? This is a, what kind of edge this is? This is a, again cross edge, right? Again cross edge. Okay, cool. So basically now you know that how to classify the edges. Let's just go to this question. What they're saying, the discovery time and finish time are given to you. Okay, classify the edges. Based on this particular discovery time and the finish time, can you tell me the edges here? What you need to do? You need to make the tree or the forest, right? So let's just make the tree or the forest, whatever is there. So let's just start from this. Let's suppose this is A, this is B, this is C, this is D. Let's suppose this is E, this is F, this is G. Anything, right? This is H. Let's suppose this is H, this is I, this is J. Okay. So let's just draw the tree. So basically you are starting at A because it is 1, right? And then where are you going? You are going to B. The tree is the directed one, right? It is a rooted tree. and then you are going to C, and then you are going to D, and then this is done, right? This part is done. Okay, and then I think you are going to this is D, that is okay. You're backtracking. This B is also done, and then you will come back to A, and then this is 8, right? You are going to E, and then you are going to F, and then you are going to, from this F where is 10, you are going to G, and then you are going to, this is G, this is 11, you are backtracking to F, and then this is H, you are going to H, from this F, then you are going to I, and then you will backtrack at H itself, right? And then you will go to F, and then, okay, so you will backtrack at F, then you are going to E, and then you are going to J. Okay, so I think this is the tree that you are getting. Now this is the tree that you are getting. Can you classify the rest of the edges? Maybe if someone asks you between C to A, if that is the edge, then what kind of edge this is? This edge is what kind of edge between C to A? Can anyone tell me? This is a back edge, right? This is a back edge. Okay, this is a back edge. Okay, let me know if that is okay to everyone. Now, interestingly, you notice one thing, that if that is a back edge, then this C, about the C and A, what can you say? That C, if that is a back edge, which means C must be descendant. See, if that is a back edge, see, between C to A, that was the back edge, right? Between C to A, that was the back edge. Okay, so maybe I can just tell you here only. Okay, just see here. If there is a back edge, then what does this mean? That C must be here because that must be descendant. A must be ancestor and C must be descendant. So that should be the relationship. So if someone tell you that there is a back edge between C to A, can't you just say that okay, that must be the relationship? And using this, can you not directly say that if that is a back edge, then the discovery time of A must be lesser than the discovery time of C. That must be finish time of C. That must be finish time of A. Can you not say this? Tell me. Which means if someone asks you that which of the following, question is that which of the following must be true for any back edge V to U, okay? Then what you will say? Let's suppose if I see B to U, which means that this is a back edge. Not the original edge. I mean, not the tree edge, which means that V to U is a back edge. So V you need to draw here, and you need to draw above, right? Now, if someone give you the options, let's suppose A, B, C, D, okay, which of the following is true about the back edge? Must be true. Then what you can say? That someone told you that okay, that discovery time of V is lesser than discovery time of U, and then finish time of U, finish time of V. Is this true? Discovery time of U can be lesser than discovery time of V, and then finish of U, and then finish of V. Is this true? Discovery time of U, and then discovery time of V, and then finish of V, and then finish of U. Is this true? Discovery time of U, and then finish time of V, finish time of U, and then discovery time of V, and then finish time of V. Is this true? So which of the following is true? Tell me. See, if someone tell you that there is a back edge, can't you directly say that this must be the relationship? Which means discovery time of U, and then V must get started, and then V must finish. So Anyway, this is not even the true. For using the parenthesis theorem, you say in between this, it can't just start, right? It must be finished also. So anyway, C is the answer here, right? C is the answer, isn't it? C is the answer. Okay, great. Now tell me, if someone tell you that there's a cross edge, okay? There's a cross edge, then which of the following is true? Let's suppose there's a cross edge, which means the cross edge between U and B must be something like this, right? Isn't it? Let's suppose there's a cross edge. Okay, let me just ask you this question. Let's suppose there's a cross edge between U and B. Then how the parenthesis will look like? Then how the parenthesis will look like? You will say, okay, U must be here, V must be here, because there is no ancestor descendant relationship, right? So neither U is coming under V nor V is coming under U. Tell me, just everyone tell me here that can it be the relation? I mean, can anyone S, can S be ruling U and V both? Can S be above U and B both? Yes, that is possible. That is possible that S can have U and B, okay, both, and then there is a cross edge between U and B. That is possible. Is it possible that U and B are not even covered by S, which means they are completely independent? Which means S is maybe here. Yeah, that is also possible that they are completely independent. U is having its own thing, V is having its own thing, and then maybe from U to B there is a edge, right, which is a cross edge. So that may be possible that S can be on above, may not be on above. That doesn't even matter to me. So basically, if there is a cross edge, then either this happen, or what is the other possibility? Other possibility is that you will say either this will happen, or maybe if there is a cross edge, then maybe this will happen, right? Okay, tell me interestingly, can this even happen? See, in the original graph, can there be an edge from U to B? In the original graph, can there be an edge from U to B? Which means, I mean, what I'm saying, it is actually given that there is an edge from U to B. Can this even possible? Is this even possible? See, if there is an edge from U to B in the original graph, which means V is reachable from U. If V is reachable, you must start it. You must start it here if it is reachable. See, what I'm trying to say, for the cross edge, actually this is not possible. Only this is the possibility, because the edge is from U to B. And from V, this U is not reachable. From this V, this U is not reachable. That is the only reason that you got the cross edge, right? I mean, you must be starting V first and then you need to start U. So basically, if U to B is a cross edge, which is given to me that U to B is a cross edge, then it must mean that this is the only possibility. Okay, then only U to B is a cross edge. Okay, in the original graph, this cannot be. I mean, if you are starting U first and U to B is an edge, then how you are starting V later on, which means even that is finished, how you are starting this V later on, that is reachable, right? If that is reachable, you must start this here. Okay, so that's what I'm trying to say, basically, that for the cross edge, this is not even the possible thing. So for the cross edge, the only possibility left is this, right? So if someone says the cross edge, right, then you will say that we will make the parenthesis like this, right? We will make the parenthesis like this, isn't it? Okay, so someone says the cross edge, then also you can say that, okay, if U and B is a cross edge, then this must be the relationship, which means you must start it, you must finish it, you must start it, you must finish it. Then in previous question, option will be A, because edge from V to U. Let me just check. Your edge is from V to U. That is a back edge, right? That is a back edge. There is an edge from V to U. So you must be starting this. The option is C only. Option is C only. You must be starting U first. Edge is from V to U. Yeah, edge is from V to U. I agree. Okay. So for the cross edge, see, for the cross edge, you must, if there's a U to B is a cross edge, then you must be having this kind of relationship. So let me just summarize. For the back edge, let's suppose A to B is a back edge. Then what is the relationship? If A to B is a back edge, which means that must be descendant, that must be ancestor, right? Okay, that is the relationship. Okay, now you tell me for cross edge. This time let's just say P to Q or maybe U to B or whatever, right? Let's just say U to B, which means if that is the cross edge, then there's, first of all, there is no relationship between U and B because that is a cross edge. Okay, I mean neither one is descendant nor one is ancestor. Okay, first of all, there is no relationship. Second thing is that if there's an edge, okay, whatever, cross edge or whatever, in the original graph there's an edge. In the original graph there's an edge, then you can't start this U. So that must be V and that must be U. Okay, if you are starting this U first, then basically you won't be getting the cross edge. You will be getting even the tree edge. I mean, this cross edge will get converted to tree edge, which means you must be starting here. I mean, you won't be getting this as a cross edge. But it is given that if it is a cross edge, you must have started this V first. Then only you are starting U, right? Then only you are not getting any relationship. Okay. Okay. Now let's just see what about the tree edge. What about the tree edge? If let's suppose U to B is a tree edge, if this is a tree edge, then U must be like this and V must be like this, right? What about what is the final edge? Forward edge. Right? What about the forward edge? Again the same thing, that if U to B is a forward edge, then it means V must be descendant, right? V must be descendant. Okay. Something like this. Understood? So basically for every type of edge, there is a fixed parenthesis. Okay. So this parenthesis and edges are also very much related. For every type of edge, there is a fixed parenthesis. Understood? Cool. Now let's just go to the next slide. Okay. Now that was the directed graph. But in undirected graph, there is a tree edge. Obviously, like tree edge will be there. See this, what they are saying, that either there will be a tree edge or there is a back edge. So there is basically, in undirected graph, there is no cross edge. Can anyone tell me why there is no cross edge in undirected graph? Why that is the reason that there is no cross edge in undirected graph? See here, what is a cross edge? See, let's suppose you have the tree, right? You have the tree. Now the cross edge will look something like this. Maybe something like this, right? You will say there's a forest that you are getting, and let's suppose this is a cross edge. Okay, there's a cross edge. See, I am making the direction in the tree. Okay, in the tree or in the forest, I am making the direction, but that is not the direction in the graph. Okay, the graph is undirected. Right? Now, can you tell me if you have some edge, something like this, which is basically cross edge, is this possible in undirected graph? See, these kind of edges are not possible. Why? Can anyone tell me? The reason is that, see here, let's suppose this is my tree. Okay, this is my tree. And let's suppose there is some cross edge, okay, which is this. See, in undirected graph, this is in the tree I'm having the direction, or in the forest I'm having the direction, but in the graph actually there is no direction, right? So which means this is the forest DFS, right? DFS forest. But in actual graph there is no directions. So this is not the direction in the actual graph. The edges are there, but there is no directions, right? Okay. So there is no directions in the actual graph actually. Okay, so basically in the actual graph, it is looking like this, isn't it? This is the graph. This is the real graph, and or the, you can say, the actual graph. In the actual graph, there is no directions. Is this okay to everyone? And in the DFS, I'm just making the direction. Okay, this is called directed tree or something. So anyway, a rooted tree or something. But what I'm saying here is that in the actual graph, since it is undirected, there is no direction. Tell me, can you have the cross edge? The answer is no. See, the reason why we were having the cross edge earlier is because, let's suppose you are exploring this, and let's suppose this is the only graph, okay? Then you have to, if that is a direction, okay, if that is a direction, you have to backtrack. But let's suppose this is not a directed, okay? This is not the directed. Then you can definitely go here, isn't it? So you will not be having the cross edge. The reason why we are having the cross edge earlier, see, in earlier also, let's suppose this is directed, okay? Tell me, in the directed graph, let's suppose I give you two cases. In the directed graph, if let's suppose I'm not writing all the edges, I'm just making the direction of one. Let's suppose this is the direction, okay? This is the case 1, this is case 2. In the directed graph itself, you tell me that if you are having this kind of, okay, first you go here, if you are having this kind of edges, will this be cross edge, or you will widget it, right? You will widget this, and then you might be widgeting this, right? So this edge won't be the cross edge if that is the direction here. In the directed graph also, if the direction is this, will this be a cross edge? No. But in the directed graph only, if the direction is this, and let's suppose you're starting from here, and if the direction is this, right? Then after going this, you have to backtrack, right? You have to backtrack. So that's why it became a cross edge. Because the direction was this. But in directed graph also, if this is the direction, it will not be the cross edge, right? Similarly, in the undirected graph, since there is no direction, so there won't be a chance of cross edge, because I will anyway widget it. Okay, so in the undirected graph, if the graph is undirected, then this edge cannot be the cross edge. Why? Because I will anyway widget it. I will see either that is reachable or unreachable. So see, the cross edge means that these two doesn't have any relationship of ancestor or descendant, right? Ancestor descendant is relationship is not there. But in the undirected graph, I will make it either ancestor or descendant. Because I will go here and I will go here, right? Why will I backtrack? Why will I backtrack from here only? Obviously, I will go here. So basically, there is no cross edge in the undirected graph, which means if you are going like this, then you will definitely widget it, right? And then you will go here. Maybe you can backtrack. You will go here. Yeah, understood. So there won't be a cross edge in the undirected graph. Okay. So that is one thing that I would just like to point out, that there is no cross edge. Okay. Now in the undirected graph, interestingly, see here, let's suppose this is the graph that you have, okay? Let's suppose this is the undirected graph that you have. Suppose you are widgeting this. This is A, this is B, this is C, this is D, this is E, this is F. Suppose you are widgeting this, and then you are going here, and then you are going here. So how your tree will look like? You will say this is A, then this is B, and then this is C, right? This is a tree. Now you tell me this edge you have encountered now, right? This edge you have encountered. So since there is no directions here, that's why you are free to choose the direction, which means you can make in the tree. You can say, this is like this, or maybe this is like this. So basically, in the tree anyway, this edge is not there. But in the graph, that edge is there. What kind of edge you will call it? See, this is definitely ancestor. This is definitely descendant, right? There's a edge between ancestor to descendant, but the direction is up to us. Maybe I can make it like this. I can call it forward, or I can call it backward. Which one would you like to call it? When you discovered it, see, have you discovered it at time of A, when you were standing at A? If you have discovered it at the standing of A, then from this A, you could have gone directly to C, right? Using this edge. Using this edge, you could have directly gone to C. If you have discovered this at A, you have discovered that at C, that okay, this is widgeted. You have discovered at C, and now I think everything is widgeted. Let me backtrack, right? So since we have discovered it at C, that's why I will like to call it as a back edge. Okay, I will like to call it as a back edge. It is just up to us, but people have defined this as a back edge. Okay, this edge could be forward or backward, but by the standard terminology, we are defining this as a back edge. Why? Because we have discovered this at the time of C. At the time of C, we have discovered it. That's why people have called this as a back edge. So see, in undirected graph, you can say back edge and forward edge is same basically. Okay, which means if this is ancestor, this is descendant. If there's an edge, you call it backward edge, forward edge, doesn't matter. Okay, so this is ancestor, this is descendant. But people have called it, okay, but standard terminology is that people have called it as a back edge, okay, as a back edge. People have called, because back edge is actually important to us also. Okay, I mean, they are very clever. The back edge is there to detect the cycles. So back edge, if in undirect or directed, whichever graph it is, they will call it that if back edge is there, then cycle is there. So they're very clever. Okay, so I mean, there is no property or there is no application of the forward edge as such. So they have said, okay, let's not call it forward edge, let's just call it back edge. Okay, so they're very clever. They because there are properties. I mean, see, they're property of the back edge. Now, if they call it forward edge, then they have to define separately that, okay, in the directed, if there's a back edge, then this is the property. In the undirected, if there's a forward edge, because back edge is not there, let's suppose, then this is the property. So that's why they made it consistent, because back edge is actually this name will be consistent for the many applications. So they are also calling it a back edge only. Okay, standard terminology. Okay. Okay, so basically you can say that in the undirected graph, there is only tree and back edge. There is no cross edge. There is no forward edge. Obviously, here you have everything, but important. I mean, forward edge is actually, I mean, that's okay, but most importantly, no cross edge. Okay, this is important. Okay, this is important. Okay. Now, there is one PYQ. Let's just solve this PYQ. So what they're saying, in a DFS, in this graph, if you have n vertices, k edges and mark as t edges, okay? So there are k tree edges, the number of connected components. So actually, this is not directly related to DFS, BFS, but let's just solve it. It is a graph theory question, by the way. But it was given in the algorithm in the GATEOverflow book. In the GATEOverflow book, it was tagged as algorithm. So I have taken it. This is easy question. Okay, easy in the sense that if you have gone through the graph theory, then this is easy question. Okay, what they're saying that they are having k edges in the forest. Okay, in the DFS traversal of the graph, n vertices, k edges are marked as t edges. The number of connected components. So see, let's suppose there are x connected component, which means this is one tree that you are getting. Okay, one tree that you are getting. This is another tree. Let's suppose there are x such trees. So what I'm saying, let's suppose there are x such trees. Okay. Combinedly, all are having k edges. Let's suppose it is having k1 edge and even k2 edge and so on. And let's suppose this is x, this is kx edge. So combinedly, all are having how many edges? K edges. It is given to us. Okay, it is given to us. The combinedly all are having k edges. Okay. Now you tell me that how many, what they are saying, how many components are there? So basically they are asking the value of x. So how to find out this value of x? Okay, can you tell me how to find out this value of x? So basically let's just assume that there are x components, and then they are only asking about the number of components. They have given the total number of edges is x. Okay, see, how many nodes will be there? If there are k1 edges, then how many nodes will be there? See, let's suppose this is 1, 2, 3 edges. Then 1, 2, 3, 4 nodes, right? So if there are k1 edges, then k1 plus 1 nodes are there. Similarly, k2 plus 1 nodes are there. So basically, if you sum up all the nodes, that must be n, right? N is given here. So k1 plus 1 plus k2 plus 1. Similarly, kx plus 1. That must be equal to n, right? That must be equal to n. So if you see here that if you put this 1 plus 1 plus 1 is nothing but x. So this k1 plus k2 plus kx is nothing but capital K, plus this, all the ones are x only, x equal to n. They have asked about the x, which is n minus k. Okay, x will be n minus k. So basically there are n minus k components are there. Okay, Easy, but nice question. It is famous property in the graph theory. In the graph theory, I'm 100% sure you must have seen this, right? This is a famous theorem in the graph theory, or the famous property. Okay. Okay. So now let's just see the applications of DFS. Okay. Let's just see the applications of DFS. Now, there are many applications of the DFS. Okay, connected components, articulation point, bridges, by connected components, and the undirected, and the directed also there are many, many are there. But in this particular session or in the class, okay. So see, I mean, some applications are actually can be done using DFS and BFS both. Okay, so but in the class we will see deducting cycles as one application, topological sort, cut vertex. Okay, because like there are many applications, we will just see whatever the standard ones. Okay, in the sense that are frequently used. Okay, so see, let's just see the DFS application one, which is cycle deduction. Okay, which is a cycle deduction. Now see this meme, what it is saying. It is saying that we can definitely check package type after a DFS, right? So this guy is saying, so what? Okay, a graph is having cycle if and only if DFS has a package. Oh, that's useful. Right, now see the expression. He's saying, okay, that's useful. So basically, this theorem is extremely important. The graph is whatever the type of graph, whether directed, undirected, doesn't matter. Whatever the type of graph, a graph is having having a cycle if and only if there is a package. If and only if. Okay, we can prove this also. I mean, the proof won't take much time, but I think it's not required. Let me just try doing it quickly. Okay, just in 1 minute. See, if there's a package, then there must be a cycle. Let's just prove this. Okay, this implication is easy implication. Let's just prove it. See, package means what? Package means what? See. It means it must be between the descendant to ancestor, like this, right? So if it's a descendant, then there's a path from ancestor to descendant already, and using package there is one more path. Right? See, this path must exist because there's a relationship like as an ancestor to descendant. So that path must exist. So that's why if there's a package, then there's one more path, right? So that's why there's a cycle. Easy, right? Very easy. Now if there's a cycle, that must be because of the package only. Can you prove this? If there's a cycle, which means the other direction is that, then there must be package only. Okay. Which means, let's suppose if there's a cycle, let me just try proving it. Let's suppose there's a cycle. Okay. Then there must be the package in the cycle. I will just give you glimpse that how can we prove it quickly. See, let's suppose this is a cycle. Then I will always prove that there must exist some package. How? See here. If this is a cycle, let's suppose in this cycle you can start from any node. Let's suppose you are starting at this node. Okay, you can start from any node because this is a cycle. Then you will be going here, and the moment you reach here, you will backtrack, right? But what about this edge? This edge will be the package. If there is a cycle at the end, somewhere there will be the package, right? You will classify one of the edges as a package, right? So see here that let's suppose in this cycle you start from here. Then what you will do? You will, let's suppose, keep on doing it. You will classify this as a package. So if there's a cycle at the end, you have to classify one of the edges as a package. This is just an intuitive proof that I want to give you. In the course, we have done the exhaustive proof, but that's not required here. Okay. Even if you have forgotten this, that's completely okay. Okay. That's not even required here. Okay. So interestingly, if there's a back edge, then there can be one or more cycles also. How? See here. See, suppose there is a package. Okay, I mean, let's suppose this is the package, right? How many cycles are here? You tell me. Everyone just tell me quickly how many cycles are here. Just one cycle. This is the cycle, right? Only one cycle. But just because of this one package, let me tell you, there could be multiple cycles also. Just because of one package. How? Can you guess it? Because of one package, how there could be multiple cycles? See, what can happen? You may be having something like this. See here. You may be having one more edge, something like this, right? Now, see, this is also the cycle, right? This is also the cycle. Or maybe just to simplify, let me have this as edge. Then this is also the cycle, right? This is also the cycle. So basically, if you are having something like this, then let's suppose this is A, this is B, this is C, this is D. Then A, B, C, D, and then A. This is a cycle. What else? A, C, D, and then A. This is also the cycle, right? So just because of one package, there are two cycles. Can there be three? Maybe. Let's suppose this is also the edge, right? Then what is the other cycle? Just because of this package, what is the other cycle? So see, if there's a package, then there will be a cycle, but there could be multiple cycles also. That's what I'm trying to say. See, A, D, and DA, right? This is another cycle. So one package can lead to one or more cycles. That's what I'm trying to say here. Okay. So package means cycle, but one package may lead to multiple cycles also. Okay. So one package at least one cycle, two package at least two cycles. Okay. So three package at least three cycles, three package at least three cycles, isn't it? And so on, right? Okay. Now you solve this question. What they're trying to say, consider the following graph. Can we pick a single edge to destroy all the cycles? Can you see this is having two packages, right? This is a package. This is a package. Can you just remove one of the edge and destroy all the cycles? No, right? Even if you remove this package will be there, and package means cycle. If you remove this package, then this package will be there, and package means cycle. So basically, you can't just remove one package. I mean, if there are multiple packages, you can't just remove one edge to destroy all the cycles, right? Because if you remove this, then this package will remain. If you remove this, then this package will remain. So it will create a cycle. So there two packages are there. So can we pick single edge to destroy all the cycles? The answer is no, right? Because there are two packages. You have to remove all the packages, right? You have to remove all the packages. Okay. Now let's see this. Can we pick a single? Okay, sorry. So here it seems like answer is no. Okay, I'm sorry about it. So but it is interesting question. Okay, but before that, maybe I can tell you this. See, can we pick a single edge to destroy all the cycles? See, this is a package, right? This is a package. If you remove this package, then you will be removing this cycle, but this cycle will remain, and vice versa. So here the answer is definitely no. But here, if you remove, okay, let's suppose this edge itself, okay, let's suppose you remove this edge itself, okay, you modify the graph, you remove this edge itself. Then do you have the cycle? No, right? You don't have the cycle now. See here, you are going from here to here, and there is no cycle. So basically, if you try to remove the package, see, if you try to remove the package to destroy all the cycles, then obviously you have to remove all the packages. But sometimes, okay, see here, sometimes it is possible that both the cycles are sharing just one edge. I mean, both the cycles are sharing some edges, right? You can remove the shared edges, which means, what I'm trying to say, understand this carefully, that one thing is for sure, that if there is a one package, which means there will be at least one cycle. Okay. For example, this is A, this is B, this is C, this is D, and so on, right? If there is a one package, then there is one cycle. Okay. Now you tell me, can there be multiple cycles? Yes. How? Just because of one package, there are multiple cycles, right? So here the cycles are AC, D, and then A, right? ACDA, basically this is a cycle. One other cycle is AB, C, D, and A. Okay. One package is leading to two cycles. Okay, one package. One and two cycles. Okay, at least one cycle will be there. Now, are there common edges in these two cycles? See here, is this common edge? I think there are common edges, right? In these two cycles. So basically, obviously you remove this one back edge. This one back edge is also common. If you remove this, are you destroying all the cycles? Yes, because there is just one back edge. You remove that back edge, you are destroying. But even if you remove this, then also you are destroying all the cycles, right? It seems like you're destroying. Or even if you don't have C to D, then also you are destroying all the cycles. So what I'm trying to say, that one back edge may lead to multiple cycles. If you want to destroy all the cycles, if there is only one back edge, you can destroy this. But if there are two back edges, okay, you can destroy this, I mean, or this, okay, or I mean, that is actually destroying the cycles. But if there are two back edges, okay, let's suppose there are two back edges. Let's suppose that there are two back edges, okay, then at least two cycles will be there. Maybe this is another back edge, okay. What is the another cycle? You can say B, C, D, and B, right? So B, C, D, and then again B. So this is another cycle. Now there are two back edges, right? Now in this case there are two back edges. Can you just pick one of the edge and destroy all the cycles? This is little tricky. See, if there is only one back edge, can you pick one edge and destroy all the cycles? Yes, you can anyway pick the back edge and you destroy all the cycles. If there are two back edges, then just one edge. Can just one edge destroy? Here, yes. What is that edge? This CD, because this is common, right? Whatever is a common edge in both the cycles, you can pick it. It can destroy both the cycles. So if there is one back edge, you remove it, all the cycles are removed. If there are two back edges, then if there's a common edge, it can destroy all the cycles, right? And all the cycles, if there is a common edge. If there is no common edge, which means if that's the case, if there is no common edge, maybe you can have something like this. If there is no common edge in both of the cycles, then you can't destroy just using one edge. Okay, then you can't destroy just using one edge. So basically, this is here, the cycle is this, right? Here C, D, E, and then C. So here can one edge? So see, in both the cases, two back edges, right? Can one edge destroy all the cycles? Here, yes, one edge can destroy all the cycles. Here, no, okay, no, because no, one edge cannot destroy all the cycles. Yeah, basically it depends. Here, if you remove this BC, then cycles are at least intact, right? Cycles are at least intact. So here it seems like that one edge cannot destroy all the cycles. Okay. Here, yeah, BC is also common. You can remove the BC and one edge can destroy. So basically, see, if there is one back edge, obviously this removal of this will destroy all the cycles. If there are two back edges, then maybe one can destroy all the cycles. Maybe one cannot destroy, right? Okay. So I hope now you understood that if there is a one back edge, then at least one cycle is there. Single edge can destroy all cycles, right? Single edge. Okay, if there is one back edge, then single edge. And what is that edge? Always back edge. Okay, back edge can always destroy. Back edge can always destroy. Now, if there are two back edges, at least two cycles, single edge may or may not destroy, right? Single edge may or may not destroy. Understood? So now you solve this question. That question is from MIT. So what they are saying, this is very interesting question. If a depth first search on the graph produce exactly one back edge, then it is possible to choose edge such that removal of this edge is acyclic. So they are saying that it has exactly one edge, okay, exactly one back edge. Then removal of there exists some edge whose removal will make it acyclic. What do you think? Whose removal will make it acyclic? This is true or false? That's what you need to tell me. This is true or false? Okay, then answer is true. If there is single package, then yes, which means it is true. What about this question? Again from MIT. What they're saying? But can be made acyclic by removing one edge? Then DFS will encounter exactly. Okay, that's interesting. That's interesting. What they're saying that can be made acyclic by removing one edge. There is a graph that can be made acyclic by removing one edge. Then the depth first search in G will encounter exactly one edge. Can you say the reverse implication that can be made acyclic with removal of one edge? Does this mean exactly one edge? One back edge? This is true or false? That's what you need to tell me. This is true or false? What do you think? This is false, right? This is false. If it is removal of one edge, then maybe there are two back edges, right? Maybe there are two back edges. Okay, so this is false. Great. I mean, we have seen, see, removal of one edge. Here also the removal of one edge. Here also removal of one edge destroying all the cycles. But it doesn't mean that there is only one back edge, right? So that's why it is false. It is false. See, removal of one edge is destroying all the cycles. It doesn't mean there is only one back edge. There are two back edges, right? I'm not removing. Okay, here. Interestingly, here I'm not removing. There can be made by removal of one edge. I'm not removing the back edge. The some other edge I'm removing. If I'm removing the one back edge, okay, then let's suppose there are two back edges and I'm removing one of them, then it doesn't make it acyclic, right? Then it doesn't make it acyclic. Is this okay to everyone? Let me know. That they have given the reverse implication. They are saying you are making it acyclic by removing one edge. See, you are making acyclic here. Here also you are making acyclic by removing this edge. Does this mean it has only one edge, one back edge? No, right? It doesn't have only one back edge. It has two back edges, even though you can make it acyclic by removing one edge. Okay. So we have talked about cycle and all. On the opposite end, let's just talk about the graph with no cycles, which means let's just talk about directed acyclic graph, which is also called as DAG. Okay. So the application 2 is topological sorts in graphs. Okay, in basically directed acyclic graph. So what is the application number 1? Cycle detection. Okay, if there is a back edge, then cycle, right? So this is application 1. Application 1. Back edge where? I mean, in which kind of graph? Directed or undirected? In which kind of graph we are talking? So here it is irrespective of any graph, okay? If back edge in any kind of graph, okay? In directed or undirected. Okay, any. But this topological sort, this has been defined only for directed acyclic graphs. So that's why we will only talk about the directed acyclic graph here, okay? We will only talk about the directed acyclic graph. So I hope you know what is the topological sort, right? So for example, here it is a directed acyclic graph. The topological sort, if you want to find out, then maybe you can start with this one of the things like, okay, pant, like you will be maybe wearing the pant first and then wallet and keys, and then putting the wallet, right, wearing the belt and then putting the shoes and so on, right? So maybe you already know that what is a topological sort, right? Okay, so if you want to find out the topological sort, maybe you can say this is U, okay, and you remove this U, and then maybe you can have V, okay, and then you can have V, you remove this U and V, and then you can have probably this W, right? you can have W. And if you remove all of this, then maybe you can have Y or Z, whatever, Y, Z, X or something, right? So basically this is one topological sort. Okay. Now let's just see this, what they are saying. Consider the directed graph given below. Okay, which of the following is true? The graph does not have any topological sorting. I think you can do this as an homework. This is easy question only. Okay, you can do this as an homework. Now in a directed acyclic graph, as we have seen, that finish time of this will always be larger than the finish time of this, right? Which means it will be finishing later. See, if there is an edge which is U to B, then can you say anything about the start time? Who will be starting first? Okay, maybe this S is connected to U, or maybe this S is connected to B. You don't know, right? Whoever can start first. But who will be finishing last in between U and B? Obviously, you will be finishing later, right? You will finish later. Okay, you will finish later. About the start time, we cannot comment about the start time, but we can definitely comment about the finish time. Okay. Now you tell me, in any graph is this okay? In any graph, we will always have the finish time will be, I mean, it will be finishing later. In any graph for any edge U to B or A to B, in any graph can we say it need not to be, let's suppose, directed acyclic graph. In any graph, okay, need not to be DAG. Need not to be directed acyclic graph. In any graph, is this true? The answer is no. Why? Because it may so happen. See, earlier that B to A path was not there, right? Because it is acyclic. If that path is there, then it will be cyclic. But if the cycle is there, then what can happen? Maybe let's suppose you are not you don't know, but let's suppose that you are starting this B first, right? This V can, you are starting this V first, and then B can be discovering this A, and this A will get finished, and then B will get finished, right? It may so happen that you are starting this B first, and this B get this A you will be starting in between, right? Maybe you can start this A in between. See, because there could be the cycle, that's why you can start this A in between, right? So it need not be the case that you will be finishing this A first, or sorry, this B first always, because there could be the cycle. So in any graph that is not the case, but in the directed acyclic graph we know. In the DAG only, in DAG, the directed acyclic graph, we know that if we are having some edge A to B, then since there is no path from B to A, okay, that's why either you start A or you start B, doesn't matter, but let's suppose you are starting A first, then this B will get finished because that is reachable. If you are starting B first, then this B, I mean, you cannot start this A after this B. So basically this A will always finish later on, okay, which means A will finish later here, A will finish later here, okay. I mean, if you are starting B first, then also A will finish later. If you are starting A first, then also A will finish later. In any graph, there could be the case that there is a path, so in between you can start this A, right? So that's why in any graph it is not true, but for the DAG it is also true. It is always true. Okay, yes. In the cycle it will fail. Okay, so this question we have already done, right? We have already done this question. Okay, they are asking about the relationship between this thing. Okay, now let's just see topological sort of DAG using DFS. See here, what we can do, we can call DFS to compute the finish time, okay, for every vertex. Now once we have the finish times, see here, let's suppose this is some DAG or something, okay, for every vertex we will be having the finish time. Can you randomly tell me that this will be finishing later on this, right? And this will be finishing later than this. So can you randomly tell me some time? So it will be finishing at last. So let's suppose this is 50, right? It will be finishing at last, right? This is the finish time, finish. It will be finishing at last. Why? I mean, not at last. So basically you can say if that is the edge, then it will be finishing at last, right? Now you can say that, okay, with this edge, see, let me have the edge by edge. See, let's suppose this is the graph that we have, okay, the directed acyclic graph. can you write the finish times? Okay, that's what I'm saying. Can you write the finish times? See, if this is, let's suppose, if this is if this is, let's suppose 10, then what can you say about this? It will be definitely greater than 10, isn't it? Because this has to be greater, right? So let's suppose this is, I'm just writing a random number, 15. If this is 10, can you not say this will be lesser or greater? See, about this is what you say. This must be greater. This must be greater. So this will be lesser. Maybe 8, right? And then what about this? What about this? This will be even lesser. Maybe 6 or something. Right? What about this edge? This edge? This, I mean, this is greater to lesser, right? So basically, I mean, this random numbers are satisfying, I think, right? If you only write the finish time, I think these random numbers are satisfying using what we have seen, right? So basically, if you notice that the highest finish time, if you start, I mean, in the topological sort, this is the highest finish time, right? And the next finish time, and the next finish time. So what we can do, if I want to find out the topological sort at every vertex, the finish insert in the front of the linked list. So basically what we can do, the highest finish time, if the highest finish time is first node in topological sort. Which means if I am finishing later, if I am finishing at last, it means what? It means that all of my dependents have been finished, and then only I can finish, right? Then only I can finish. All of my dependents have been finished. So basically, I am not dependent on anything. See, if I'm the highest one, if I'm finishing at last, which means you understand, ये like it's like that, ये घर के बड़े लोग हैं, है ना? बड़े लोग means like our parents or something. So basically, generally our parents do what? They say that, okay, if all of you are done, let's suppose having the dinner or having the lunch, then only I will have the dinner, something like that, right? So if all of you are satisfying your requirement, all of you are done, then I will be doing something. So basically, if I'm finishing at last, it means what? It means that there is no dependent on me. I mean, see, the dependent finished earlier, right? So if that is the edge, then you will say that this will finish later. So whatever is finishing later is basically a first node to me as a topological sort. So what we can do, run DFS, then sort in descending order. Of finish time, and then we have our topological sort. Right? So basically, you don't even need to sort. Whoever is getting finished, let's suppose this is getting finished, you can put it in the array or in the queue or something, or maybe in the linked list. Okay, whoever is getting finished, then you can put that in the linked list. Okay, A has been finished. Then let's suppose after that, let's suppose this B is finished first. Then let's suppose this B is finished. Then after that, let's suppose A is finished. Then you can keep on putting in the front of the linked list, right? Then let's suppose this S is finished. Then ultimately this linked list is representing your topological sort. So basically this idea of that, okay, this edge, this is always having the higher finish time. This idea can lead to the topological sort itself, right? So what they are saying, that in the, like, you run the DFS and whoever is having the highest finish time is the first node, then second highest, the second node in the topological sort, and so on. Okay. So that's the chronology. Okay. So आप chronology समझिए. Now let's just move to the third, that is most interesting application, and little tough also, but we will make it very, very nice. Okay, most interesting application, third and most interesting application of DFS, which is articulation point or the cut vertex. Okay, let's just see this articulation point or the cut vertex. Now if you see this, that we have done the redirecting cycle, finding topological sort. Let's just see the last one, which is cut vertex in the undirected graph. So basically in the directed, there is no well-defined definition of the cut vertex. So that's why we will just see the undirected graph here. Okay. What is the articulation point or the cut vertex? Let's suppose if this is the graph of undirected graph, then if you remove this, then it will disconnect this graph, right? So that's why 2 is the articulation point. Similarly, what else? Similarly, what else is the articulation point here? Can anyone tell me? Apart from 2? Let me know. Yeah, 6 is also right. Okay, great. So basically 6 is also the articulation point. Now how to find the articulation point? Okay. See, brute force approach is that you can remove it and see if all the vertex is reachable, right? Okay, remove a vertex and run DFS or BFS to see if all vertices are reachable. All vertices are reachable. Okay, you can do this. Remove a vertex and see if all vertices reachable. But if you do this, then what is the time complexity of BFS or DFS? The both are having the same time complexity, which is order of v plus e. And if you do it for all the vertices, then into v, right? Into v. So it is almost v square. It is too much. We can just do it in v plus e. Okay, we can just run the BFS one, DFS one. So basically, we can just run DFS once and detect the cycle. Sorry, and find cut vertex. So it is cut vertex. Find cut vertex. That's very nice, right? So just once. What is the time complexity if you do it? Then it is order of v plus e. Okay. Let's just see how to do it. See, this is a DFS based approach. Okay, this is going to be the DFS based approach. Now in this approach we are going to see that how to find out the articulation points. See here that let's suppose I make the this directed tree of this particular graph, which is a DFS tree. Okay, let's suppose I choose 2 as a root. First of all, tell me is a 2 articulation point. Yes. Now if I'm choosing 2 as a root, then what is happening? Then this is something that I'm getting. Now you tell me, is this 2 articulation point? I mean, looking at this, can you now tell me? Looking at this tree and the extra edges, whatever is there, can you now tell me that 2 is an articulation point? Suppose I don't give you the graph, I give you the graph in this form, which means I give you the tree and the dotted edges, right? Then can you not tell me 2 is an articulation point? Definitely, right? But what if I have something like this? See here, what if I have something like this? Let's suppose this is the tree that I'm getting, but the actual graph was like this. Okay, there is a cross edge. Okay, the actual graph maybe the cross edge between 2 nodes, maybe from here to here. Then is 2 articulation point? If there is a cross edge, then there is no articulation, then 2 is not articulation point. But if there is no cross edge, then 2 is articulation point, isn't it? If there is no cross edge, then removing this 2 will disconnect, right? If there is no cross edge, if there is no one else is connecting, then removing this 2 will definitely disconnect. But if there is a cross edge, then this 2 is not articulation point. But interestingly, in undirected graph there is no cross edge, isn't it? See, in undirected graph, if there is a cross edge, then this will, this cannot lead to, this cross edge cannot be there in undirected graph. We have seen this, that why cross edge cannot be there. In undirected graph, this cross edge cannot be there. See, what I'm trying to say here is that this 2 can be articulation point if there is no cross edge, right? I mean, these two components are not connected using any other edge. So I can say 2 is articulation point. But since there is no cross edge anyhow, then 2 is always the articulation point, isn't it? See, when can, if I just ask you, when can the root of the DFS tree be articulation point, then what you will say? When can, if I just ask you, when can root be the articulation point? It seems like always, right? I mean, because there is no cross edge, then always. But there is a small condition that if that is having multiple child, right, or multiple children, if that is just having one children, then how it can be the articulation point, right? So the only thing is that must have more than one child. For example, let's suppose I make a DFS here, okay, using 1 as root. Okay, let's suppose 1 is root. Then from this one, you will go to, let's suppose 2, then 2, 5, 6, 7, 8. Okay, then from this one, you will go 2, 5, then 6, 7, and 8. Okay, 1, 2, 5, 6, 7, 8, and then you backtrack, and then from this, okay, from the 6 you are going to 4, and then you backtrack, okay, and then from this 2 you will go to 3. Okay, from this 6 you will go to 4, and then from this 2 you will go to 3. Anyway, so this is the tree that you will be getting. Now tell me, in this tree, looking at this tree, can you tell me, is one articulation point, is root articulation point? See, articulation point is 2 and 6 only. Okay, it's not like that whatever root you are choosing, it will become the articulation point. It's not like that. See, if 1 is not the articulation point, then it will only be having one child. Okay, it will not be having multiple children. One subtree only it is having, right? It is not having multiple children. You pick anything other than 2 and 6. You pick anything other than 2 and 6. It will not be having multiple children. You pick anything other than 2 and 6, right? So for example, if you pick, let's suppose if you pick 7, right? If you pick 7, then what will happen? Then it will be just having one children. I'm 100% sure about it. Then 7 to 2, you can go to 6, then you can go to 5, 7, 6, 5, 2, 1, 3. Let's suppose 7, 6, 5, 2, 1, 3. And then, okay, then from this 7, 6, 5, 2, 1, 3, that is okay. Then you backtrack. From 2, you will go to 4. And then from 6, you will go to 8. Okay. 4, from 6, you will go to 8. Even if you pick 7, only one child, right? Because that's not the articulation point. But if you pick 6, then there will be more than one child. See here, if you pick either 2 or 6, if you pick 6, then what will happen? Then you will go to maybe 7, then you will go to, let's suppose, 8. Then this is complete, right? Then you will backtrack. Then you will go to 4 or 5, whatever, right? 4, then probably you will go to 5, right? Then you will go to 5. So from the 6, 4, 5, then 2, 1, 3 or whatever, right? Okay, 2, 1, 3. See, if you are picking 6, then automatically you are getting 2 child. Okay, 2 children. And similarly, if you are picking 2, see here, if you are picking 2, then also you are getting 2 children automatically. So when can root be the articulation point? Whenever there is just 2 children, right? When it has more than more than one child. Why? Because there is no possibility of the cross edge. Since there is no possibility of the cross edge, then just by looking at the root, okay, can you not say this is a articulation point or not? So when can be the root of the DFT? DFT means depth first tree. Okay, depth first tree with the articulation point. Whenever root is having more than 2 children. Okay, I mean more than one child basically. Okay, 2 or more than 2 children. So basically you can say whenever root is having more than 2 child. Okay, let me know if that is fine. Okay, I mean more than one child or more 2 or more than 2 child. Okay, anyway, let me write more than one child. Is this okay to everyone? See, if 5 is not articulation point, let's suppose I ask you the question. Okay, question is that if we start DFS at 5, then number of children of 5 will be. Do you really need to, let's suppose this is the NAT question, do you really need to make the DFT to solve this question? Okay, what is the answer here? How many children this 5 will be having? How many children this 5 will be having if you make the DFS starting at 5? Definitely only one, right? It cannot have 2 because it's not the articulation point, right? So it cannot have 2 basically. Definitely 1, right? So what is the answer? Answer is 1. Okay. So they were saying that it means those having more than one child, the cross s without the cross s. See, the cross s is not even present, right? So if you are having more than one child, then automatically this is a cut vertex. Okay, you don't need to worry about the cross s because the cross s is anyway not there. Okay. Now that is about the root. So when can root be the articulation point? Whenever it is having more than one children. What about the non-root? Let's suppose 6. Okay, let's suppose I got this as a tree, and if I just ask you that can this 6 be the articulation point or anything else? What should be the condition that using which you can say that this 6 can be articulation point? See, currently it seems like if you remove this 6, then yes, it is articulation point, right? I mean, everything is disconnected. So what should be the condition? You can say that its descendant, none of this descendant should go to his ancestor. I mean, if that wants to go, then that can go through 6, okay, through 6, but it should not be directly connected. See, can this kind of edge is possible? First of all, tell me, can this kind of edge is possible? No, right? Because this is a cross edge. So only thing that you need to worry about within this tree only, right? You don't need to worry about the cross edge. You only need to worry about the back edges. Now the back edge, if that is present, then that has to be using 6, which means that there cannot be any descendant that can bypass 6 and can be connected to the ancestor of 6. If that is the case, then you can say 6 is articulation point. So when can non-root or the internal node, let me just write internal node, okay, internal non-root be articulation point? You can say whenever we have, I mean, if a node, you can say if a node does not have any edge, if a node does not have any edge from its descendant to ancestor, right? If a node does not have any edge from its descendant to ancestor, okay, its own its descendant to ancestor directly, basically, if you want. I mean, edge means direct only. Okay, there is no indirect edge or something. I mean, the path anyway. So this directly. So if they are not directly, there is no edge, then it seems like that can be articulation point. But there is one small catch here. This is little bit wrong. Okay, let me just tell you why. Okay, see, first of all tell me, if you have something like this, okay, let's suppose okay, suppose I want to check whether this is articulation point or not, and only edges that I'm having is basically something like this. Okay, only something like this. Is this articulation point? Tell me. Is there any descendant of it which is having direct edge from descendant to ancestor? No, right? So this is articulation point. This is articulation. This is definitely articulation point. Let me know if that is clear to everyone. Okay, if there is, there is no this kind of edges, right? Now suppose I have something like this. I have something like this, which means one of its, okay, one of its descendant is connected to the ancestor directly. Is this articulation point? Is this articulation point? See here, what is happening here is that let's suppose currently it is not articulation point, but let's suppose that interestingly, this is very interesting case. Let's suppose that you also have this, this is the complete graph. You also have one subtree which is satisfying this property, which means there is no direct edge from descendant to ancestor. So if you remove this, see, if you remove this, will it disconnect the graph? What do you think? What do you think? Will it disconnect the graph? Yeah, graph is disconnected, isn't it? If you remove this, then see, this part is definitely connected. Okay, this part is definitely connected using this, but what about this part? What about this part? What about this part? This part got disconnected, isn't it? So what I'm trying to say that here in our definition that we have written, that a non-root can be articulation point if does not have any edge from its descendant to ancestor directly. It does not have. But even if it is have, then at least this should be true for one subtree. Which means only thing that I need to modify here is that this is the correct definition. The only thing that I need to modify is this. See, actually in GATE 2021, I will tell you, in GATE 2021, I think, okay, 21 or 21, I think, they have asked this question. Okay, the exactly same question they have asked. So this should be true, okay, for at least one subtree. Okay, which means you tell me this. Let's suppose this is U. Okay, this is A, B, C, D, E, F. You just tell me, is U articulation point? What do you think? Is U articulation point? The answer is yes, right? Obviously, U is articulation point. Now let's just make the DFT here. Okay, let's just see what is happening. If you make the depth first tree, then what is happening? You don't need to start with U. If you start with U, there will be two children. But let's suppose I start with something else. Okay, I start with, let's suppose, A. Okay, I want U to be in between. So A to B to C to U, right? Okay, so maybe I can start from here. It will take some space. So this is A to B to C to U. Okay, now from U to D, okay, then E and F. A to B to C to U to D to E and F. Okay, so A, B, C, U. So from U to A, there is one which I have not written, right? Okay, I don't. Okay, basically, let's not start with A. Let me start with something else that can make it little tricky. Okay, so maybe, okay, just a second, just for the sake of example, I want to give you, let's suppose I want to start a C. Okay, I mean, you can start with A also, but the sequence that I want to have, maybe it will work. C to U, let's suppose, I mean, I want to have two actually child of U. Okay, two child of U. two children of U. So C to U, then D, then E, and then F. Okay, and then this will backtrack at U. You will say now it is to A, then to B, and then that's all, right? Okay. Now you see here there is one edge which is B to C, right? B to C I have not drawn. Okay, but let's just draw it in a tree. Okay, which is a back edge basically. That's fine. So see, its descendant is connected to, as per this U is concerned, its descendant is connected to the ancestor. Does this make U as a non-AP? Isn't it the articulation point just because its descendant is connected to the ancestor? No, I will not look at this. I will look at least one subtree is there such that its descendant is not connected to the ancestor. Is this true? Tell me. Yes, at least one subtree is there such that its descendant, right, is not connected to the C, right? At least one subtree is there. So that's why it is the articulation point, right? See here in this particular example, U is having two subtrees, this subtree. In this subtree, descendant is connected to the ancestor. U descendant is connected to U ancestor, which is okay. I am not looking at only one subtree. Is there any one subtree at least such that its descendant is not connected to U's ancestor? Then U is articulation point. Okay. If there is one subtree that is connected, that's okay. But at least I have one example to support me. Okay. So that's why this is true. Now you tell me this. See, that has been asked in GATE 2021. So that's why I'm little emphasizing in more. Okay. You tell me this. This is a question. Okay. I've taken one statement only. This is a question from GATE 2021, which no one was able to solve actually. I mean, I think almost 99.99% students were not able to solve this. Okay. Failed at this. You just tell me that what is the answer here. If U is an articulation point such that X is an ancestor of U, okay, use an articulation point such that it is given that use an articulation point such that X is an ancestor of U, okay, in tree, and Y is a descendant of U, and Y is a descendant, okay, then all paths from X to Y must pass through U. So they are saying all paths from X to Y in G, okay, which means in the graph is undirected basically. So they are saying that if you want to connect X to Y, then they must, all paths from X to Y must pass through U. Is this true? Just think about it. Which means if you want to go from Y to X, then you must, if this is an articulation point, then you must be passing through this. What do you think? Can they be directly connected? Still it is articulation point. Yes, maybe because of some other subtree, right? Maybe because of some other subtree, it is articulation point because of this subtree. Maybe there is some other subtree. That's very, very interesting, very, very important also. See, they are saying that if U is an articulation point which is given, then it must happen that Y to X, they must pass through U. No, they can be directly connected, and it is articulation point not because of this X, not because of this Y. That is articulation point because of some other subtree. Hence it is false, right? Okay, hence this is false. What they're saying that if this is an articulation point, then you must go through U only. Yeah. Let me just modify this statement. So I will modify, but let me just explain this once more. See, they are saying it cannot be directly connected. It can be directly connected because there can be some other subtree because of which it is a articulation point, right? Now if I just modify this statement and if I say this, if I just say this, okay, given that assume, or given that, let's suppose assume U only has one subtree. Now you tell me, this is true or false? They are saying there is a X, there is a U, there is a Y. Okay, this U is having only one subtree. Okay, U has only one subtree as child. Then all the path must go through. Can they be directly connected? No. If there is only one subtree and this is articulation point, then yes, then it is true. Then it is true. In that case, it is true. Okay. Otherwise, it is false. You need to understand this. Otherwise, this is false. Why that is false? Because that may not be articulation point because of this setup. That might be articulation point because of this subtree, right? So whatever is happening to you, I don't care. Whatever you are directly connected, not directly connected, it is the articulation point. Maybe because of something else. It is the articulation point maybe because of something else. So whatever is happening to you doesn't matter to me at all. Okay. Hope you understood. So I hope I will summarize everything. Don't worry. So I hope you are trying to understand here. When can the known root be the articulation point? Whenever there is at least one subtree which I can find such that it is not connected to the ancestor, right? Okay. So you can say something like this. Okay. An internal node acts as articulation point if and only if it has a child y such that there is no back edge from subtree of y to ancestor of x. So basically it has some child y. Okay. It has some basically there exists at least one subtree, or in easy language, let me write it. Okay. In easy language, an internal node is articulation point if and only if there is one subtree that makes it articulation point, right? There is one subtree that does not connect directly to ancestor. You can say something like this, right? Some internal node u is articulation point if and only if there is some, basically it is an articulation point if there is some subtree that is making it articulation point. There is no direct jump from here to here. If you want to go, then it is like this. If there is at least one subtree, let's suppose if I say something like this. Okay, this is okay. Maybe let's suppose this is x. There is some u. Okay, there is some u. Okay, let's suppose I say something like this. There is one subtree like this. There is one subtree like this. There is one subtree like this. Let's suppose this subtree may be connecting directly. This subtree may be connecting directly. Okay, this subtree may be connecting directly, but this subtree doesn't get connected directly. At least one subtree is there. Is this articulation point? Is u articulation point? What do you think? The answer is yes. Okay, answer is yes. Understood? Because there is one subtree. See, that is not directly connected, right? So even if you remove it, this subtree at least will get removed. Okay, this subtree at least will get removed. So hence this is articulation point. Okay, so what about the leaf? What about the leaf of this? Can the leaf be a leaf of the tree be the articulation point? See, if you remove this, will anything matter? No, right? So leaf can never be the articulation point. Okay, leaf can never be articulation. Is this understood? Now, can 3 be the articulation point? No. Now let me ask you one interesting question. See here, this leaf is not articulation point. Now suppose you start this DFS on 8 only. Okay, here I have started on 2. That's fine. But suppose you start the DFS. I mean the root. If you make the root as 8. Okay. Suppose you make root as 8 only. Then can you tell me how many children this root will be having? See, if you start at 8, since you know that it was a leaf, then it is not the articulation point. Then how many children it will be having? It will be only having one children. Okay, you can do anything. 7 to 6 to maybe 5 to 4 to 2. Okay, 8 to 7, 6, 5, 4, 2, 1, 3. Okay, see here 1, 3. See, if you make it as a root, then it will only be having one children. Why? Because it was the leaf. It was the leaf in some other traversal, which means we know it cannot be articulation point. Hence, even if you make it as a root, then basically it will be just having one children, right? So what I'm saying, if I ask you the question something like this, the question is this. Suppose we run DFS and find that node A is on leaf. Now we run DFS one more time using A as start node. Then how many children will A be having? What is the answer? How many children will A be having? Suppose this is NAT question, or maybe they can give you the options, right? Maybe they can give you options. Option is saying 2 children. This is saying one child. This is saying 0. This is saying more than one. Anything. What is the answer? The answer is definitely one child, right? Only one, exactly one child. If you are starting at this particular node A, then since it was the leaf, then I know it cannot be articulation point. Hence, exactly one child it will be having, right? I hope you understood. So let me just quickly summarize everything that we have seen, right? And then we will do a question. Okay. So what is the summary? Okay. DFS articulation point summary. What is the summary? A root is articulation point if and only if it has 2 or more children, basically, right? What is the second point? Non-root and internal node is articulation point if and only if there is a subtree, okay, which is making it as articulation point. There is a subtree such that it's none of its node is connected to ancestor, something like that, right? Let's suppose you. Okay. What is the third? Leaf. What about the leaf? Leaf can never be articulation point, right? Okay. So this is the summary. I hope you understood. Leaf can never be articulation point, right? Now let's just solve this question which has been asking GATE 2021. What they are saying, articulation point they have defined, okay, whatever it is. Now they are saying let T be the DFS tree denoted by oriented by doing DFS in the connector, ठीक है? Undirected graph must be there because it is articulation point. Which of the following options is or are true? Root of T can never be articulation point. Can the root never be articulation point? What do you think? What is the answer? Let's suppose this is MSQ. So no, it can be, right? Root of T is an articulation point in G if and only if it is more than 2 children. If it has 2 or more children, yes, that is true, right? If it is having 2 or more children, a leaf of T can be articulation point. No, it cannot be. Leaf can never be. if u is an articulation point, that's what we have already seen actually. This was that statement only. If u is an articulation point such that x is an ancestor of u, okay, which means this is a setup, then all of his parts must go. No, there may be a different subtree that is making an articulation point, right? So actually, this particular statement was the most trickiest one. Okay, so this is also false. We have seen this. This was the most trickiest one actually. I hope you understood. Now we have finished. Basically, we have finished all the applications which were there in the syllabus. So all applications, DFS applications of DFS is done. And what else? Balance parenthesis or the parenthesis theorem, basically parenthesis theorem, which was the most crucial one. Okay, is done. So basically now you can solve, okay, using these two things. This is the tool of DFS. Now you can solve any question, okay, any question of DFS. This parenthesis theorem is also very strong, right? Now we have seen that, okay, when is there a cycle? Whenever there is a back edge, right? Back edge. What is the other application we have seen? Articulation point we have seen. What is the other application that we have seen? Tell me. What was the first application? I mean, the second application we have seen. It was a topological sort, right? Okay. Now there is a question which has been asked in GATE 2000. This seems to be very interesting question. Do you want to solve this question? So let's just solve one or two questions and then we can just wrap up this session, right? This is another question. So let's just solve one or two questions. So what they are saying, let G be undirected graph, consider a DFS traversal of G, and let T be the resulting DFS tree. Let U be the vertex in G and V is the first new unvisited vertex after visiting U in the traversal. So they are saying let U be the vertex, okay, and V is the first new unvisited vertex after visiting U. Okay, so which means you are visiting U. Now it might be the case, see, you are visiting U, right? Which means it might be the case that you start this U and this end this U, which means that you immediately backtrack. See, you can immediately backtrack, which means that they are saying that, see, this is U, this is V, right? This is one case where you will be visiting immediately after visiting U, you will be visiting V. This might be the case. Maybe this might be also the case. Okay, this edge could be reversed, which means, I mean, or may not be even edge, right? What I'm saying that you backtrack on U and then later on, okay, later on you visit U, you visit V. So basically it might be the case, what I'm saying, if you're visiting U, immediately after they are saying you're visiting V, maybe you're visiting V like this and you will obviously end at somewhere. Or maybe it might be the case that you are visiting this U, then there is no relation between U and V, right? It may be the case that they are saying that immediately you backtrack. Maybe you may immediately backtrack, isn't it? So they are saying that new first vertex that you visit after U is V. That I agree. But you may immediately backtrack. So that is why this is also possible. This is also possible, right? I mean, that can be ancestor or the parent-child relationship. That can be no relation. That can be within just one umbrella, which means like this also, right? That can be within just one umbrella. May not be one umbrella also. There's a completely different subtrees, right? There's a completely different subtrees like this. So there could be anything. But yeah, let's just read the question more. So what they're saying, which of the following is always true? UV must be the edge. So do you think UV must be the edge? No, right? It may be the case that you are immediately, this may be the case that that you are immediately doing it and there is no relationship, right? There is no relationship. So it need not to be immediately backtracking. UV must be, no, UV, if UV is not the edge, then U is a leaf. Okay, in the tree. Yeah, see, if they are saying if UV is not the edge, then U must be the, what do you think? In the tree. In the tree, do you think it is a leaf? Just try thinking it. If it is not the edge, then UV must be having the same parent in T. Same parent in T. So they are saying if it is not the edge, then they must be under the same umbrella. Under the same umbrella. So there is only one tree, right? Okay, T with the resulting depth first series. There is no forest. Okay. So first tell me, do they have to be under the same umbrella? Which means, can they be having the different parents? Which means, can this U be having a different parent? Is this possible? That U is having a different parent and V is also having a different parent. Which means maybe this U is having a different parent, V is having different parent, and both are in one umbrella. Tell me, is this possible? Okay, this is an undirected graph, right? Let's suppose this is S, this is PQ. Is this possible that they both are having different parent? Yeah, if the graph itself is like this, and then P is connected to U, and Q is connected to P, right? If the graph itself is like this, from S you will go to P, then you will go to U, and then you backtrack. Yeah, if the graph itself is like this, then they are not having the same parent. They are having the different parents, right? They are having the different parents. I mean, ultimately there could be the same node because there is only one tree, so there is just one root. But in between also they can differ. So see here, the parenthesis theorem is very nice to solve these kind of questions, isn't it? Any question, like basically there will be many questions that you can solve using parenthesis theorem. Okay, very powerful theorem. So that's why, see, must be edge, it actually need not to be true. Because see, only the counter example we have this, right? If this is the counter example for 3 options, not just for one option. See, UB is not the edge. Okay, but here, here we are not visiting immediately after U. We are not visiting this V. So maybe I can have this. Okay, this is a counter example because immediately after U we need to visit V. So that is the condition which is given, right? So U and V both are not having the same parent. It is having P as parent. It is having S as parent. Okay. So, and there is no edge which is UV. So basically it is a counter example for all of these 3. Right. See here, is UV a edge? No. If this is the graph that I have here, then is UV edge? No. U must be the leaf. That is true because what they are saying, that if UV is not the edge, then it must be the ending point, right? Because you need to backtrack here. If you are going further from here, and that has to be V. That's what they are saying, right? That's what they are saying, that V must be the first node that you need to visit. Okay. So hence need not to be the edge. It must be the leaf, because after that you need to visit V only. They are sharing the same parent. That also false, right? Very good question. But using the parenthesis theorem, actually you can draw something like this, and then you can think like, okay, which one is true, right? The parenthesis theorem is extremely helpful, isn't it? So here the answer is C, and we have solved using the parenthesis theorem. See, otherwise hit and trial and whatever you do, it will be a little tricky. So they are saying, they are talking about D and F. Okay. So anyway, whatever they are doing, let's not worry about it. But I mean, this parenthesis theorem actually, yeah, one of my favorite. Okay, in this DFS, in this DFS there is only one important theorem, which is parenthesis theorem. And let me just tell you that no one, absolutely no one I have seen who is teaching it. Okay, who teaching it? I mean, at least in the gate industry, no one teaches this parenthesis theorem. Okay, if you really like this theorem, then after the session end, please comment and show some love. Okay, and spread love. Okay, please comment and spread love. Just let me know how much you like this session. We are about to end the session. Just let me know how much you loved this session. Please comment. There should be the flood of comments so that we really get motivated that, okay, our teaching, like whatever research we are doing, okay, our teaching is actually getting reached and to the students, and students are really liking it. See, if you do not comment, then we do not get motivated. See, this parenthesis theorem I have not only just studied it, okay, or not only taught you, I have taught that many questions you can solve using the parenthesis theorem, and we have gone through articulation point very beautifully, okay, very beautiful. We have gone through this gate 2021 question is very beautiful, okay. So we have gone through these things really nice. So just let us know after the session end, okay. This is gate 2006 question. Let's just try solving it. Let T be the DFS tree in the undirected graph. U and V are the leaf of this tree. So they are saying there's a tree that you have, okay. U is a leaf and V is also the leaf, okay. Maybe they are having like this in the, okay, something like this. Which of the following? There must exist a vertex W adjacent to U and B. Okay, so they are saying U and B are the leaves of this tree. The degree of both U and B in G are at least 2. Okay, in the graph, in the real graph, the degree is 2. So they are saying U and V are basically leaves, and originally in the graph the degree is at least 2. see if this U is a leaf, okay, and this is an undirected graph, okay, if this is a leaf, if the degree is at least 2, then one is I'm satisfying like this, one I'm satisfying like this, and then other I'm satisfying like this. I mean, you can have something like this, because there is no cross edge possibility. So maybe if that is a tree, then you can have some back edge only, right? You can have you can satisfy other thing like this, okay. And if there is one more leaf, maybe that could be here, that could be here, and this is also having 2, then maybe it is also having some back edge or something, okay. There must exist a vertex W adjacent to both U and V. Okay, is this really true? Oh, I don't think so, right? See, they are saying that U and V are sharing this can be V, right? They are sharing one. There must exist vertex W, which is adjacent to U and V. Do you think? I mean, see, the degree you can satisfy 2 like this. No, right? There must exist a W whose removal disconnect U and V. What do you think? See, here it is disconnecting, but can it be something like this? If it is leaf, then it has to be here. You can't extend it. Then V can be here. Okay, and then can they be connected? See, this is connected like this. If you remove this, need not to be, right? Maybe this is also correct. Okay, see what I'm trying to say, that see, the adjacent part is okay, right? The adjacent, they need not to be adjacent, right? I mean, this is different, right? The adjacent part is okay, I think. Now here it seems that, okay, because of this parent, if you disconnect them, then U and V are getting disconnected. But is this really always true? Let's just see this. Need not to be, right? So maybe U is connected to this and V is also connected to this. So it need not to be true that there must be a W who is removal. So here can it remove? No. Can this remove U and V? Obviously no, because if you remove this, then that is there. Okay, so here in this setup, I don't think so, right? I don't think so. There must exist a cycle containing U and V. There must exist a cycle. Okay, that's very interesting. So let's just see this. There must exist a cycle containing U and V. There must exist a cycle G containing U and all of its neighbors. Okay. Do you want to solve this? Do you want to take some time and solve this? So they are saying there must exist a cycle. So what do you think? In G containing U and V. So see here. Is there a cycle containing U and V? In G, I don't think there's a cycle which is containing U and V, right? See here, there's no cycle. This cycle is different and this cycle is different. So there exists a cycle in G containing U and all of its neighbors. So what is U and V are the leaves of tree, the both of the degree, which of the following? Okay. See what they're saying. This is a little tricky question. So what they're saying, let's just try to solve this question, right? So let's just see about the cycles. Okay. Do they really need to have the cycle or not? Okay. Let's just check. So you have let's suppose that there is a graph, okay, in which U and B are two leaf nodes, right? Now they are saying that the degree of U and degree of V are at least, okay, at least these degrees are 2 and 2, which means this U is also connected to, this must be having somewhere connection, and this must be also having some connection, right? Okay. Now cycle means what? Back edge, isn't it? Back edge. You just tell me, they are saying that if the degree 2 you have to satisfy, you just tell me that they are saying that there must be back edge, right? That is starting from U, or maybe V. Actually, you can have V also here or U also here, doesn't matter. It's a symmetric situation. So there must be a back edge. What do you think? This graph is undirected, so there can be the back edge. There won't be a forward edge basically. So if the degree is 2, then it means in the graph if the degree is 2, then 1 is satisfied here. Then what it will do? There must be some other neighbors, right? What it will do? Those neighbors, if this is leaf also, then the neighbors also must have already been visited. Then this must be the back edge, right? This must be the back edge. So it must be the back edge. So yeah, that is true actually. That is true because of the back edge. See what is happening? This U is here, and now the degree is 2, which means if it is a leaf, then there cannot be more nodes in to satisfy the degree, right? The nodes which are satisfying the degree are above only, which means this is the back edge. Back edge means there's a cycle. Yeah, U and all of its neighbors. So whatever the neighbor, see this is the neighbor and this is the neighbor. Let's suppose there is other neighbor. Whatever the neighbors are there must be the cycle, right? All the neighbors are basically forming the back edge. If there are multiple neighbors, then there are multiple back edges, which means if U is here, which is a leaf, and now you need to satisfy the degree, which means there can be this back edge, there can be multiple back edges, right? This can be back edge, this can be back edge. If there are multiple back edges, there will be multiple cycles, which means here, let's suppose this is A, this is B, this is U. So A, U, okay, or whatever is in between, okay, you can say, sorry, you start with U, okay, U, and then go to A, then there's a from A to U, right? This is one cycle. If there are multiple, what I'm saying is there are multiple neighbors, there are multiple cycles, right? This U, B, and whatever in between, this is another cycle. So anyway, the back edge must be there because cycle means back edge, right? So the back edge must be there. So what they are saying, the cycle in the containing U and B. No, this U and V could be different. It could be really different story. There is a cycle that is true, but this U could be completely different from this V, right? This V and U could be completely different story, which means they are having their own cycle and all, right? This can have its own cycle. Let's suppose this is basically, it can have its own cycle. It can have its own cycle, right? They can have different cycles. It is not necessary that they are having just one cycle, right? They both are involved in one cycle, right? It is not necessary. And also we have seen other counter examples that they are saying the removal. Okay, removal means that that cut vertex, right? So for the cycle we have seen the cycle must be there, but it need not to involve U and B both. So that's why must be there, but it need not to involve U and B both. So that's why C is false, D is true. What about A and B? Must exist adjacent? No, we can have there again. This is true that for this graph there is no adjacent. Now they are saying that there must exist a W that will disconnect U and V. No, that's also not true. We have seen that it can be the part. I mean, it can be the part of same subtree, and we have seen the example here. Here, I think we have seen that U and V. There is no one who is disconnected U and V, right? So this was really a good question, which has got 88 upvotes, which means it was a really a good question. So we have solved it. I think D is the answer. Yeah, D is the answer. Okay. This is easy question only. Okay. So now we have ended the session. I mean, all the things that I wanted to discuss is finished. So we have done everything very nicely. I will just request you to put a comment, right? We have done parenthesis theorem, articulation point, very beautiful question, which is GATE 2021 question, and other questions, right? I will just request you put a comment, and after the session end, okay, just put a comment. Okay, how much you liked it. If you loved the session, just write it. Okay, that loved it, so that it get some motivation to us. Okay, so thank you everyone. That is all about the session. Take care. Bye bye. So yeah, BFS I want to be able to cover in this particular session. For that, I will be taking one more session. Okay, where I will be covering BFS and shortest path and other things. Okay, other graph algorithms. DFS was quite big. BFS is not that big. Breadth first search is not that big. Okay, but DFS was really big.